Let's start. Welcome to this workshop on how European projects are developing HPC-based software and services to address natural hazards. This is a workshop co-organized between the ChEESE Center of Excellence, the National Competence Center from Spain, and also the Work Package 3 of the Castile CSA, the Coordinated Support Action. Before start, let me just start by thanking the organizers, and in particular Ayrton Guimarães from Barcelona Supercomputing Center, and Barbara Viria from CSIC for the enormous effort that they have put on organizing this workshop. We have the last numbers that they gave me now is about 80 participants, so we will start even if not everybody is here at this moment, but I understand that they will join at some point. So this is the agenda for today. We have 8 talks from different speakers. And each talk, except the last one, is going to be half an hour, but I'm going to ask the speakers to make it in 25 minutes and leave 5 additional minutes for questions from the audience. I also ask the audience to mute your microphones, please. And also, if you have questions, feel free to put the questions on the chat, and then once every speaker finishes the talk, they will reply to your questions. Okay, so this is the agenda. I have prepared just a couple of introductory slides for people that is not very familiar with CoEs and NCCs about the European HPC ecosystem or landscape, which actually is sustained on 3 pillars: infrastructure, applications, and technology. In terms of infrastructure, it's obvious that the large-scale supercomputers, such as the one that we have under the umbrella of the Euro HPC joint undertaking, are fundamental to assess and forecast geohazardous phenomena, like, for example, earthquakes, tsunamis, or volcanic eruptions, among many others. And this is particularly true during emergency situations. We have now a quite large number of pre-exascale and petascale systems in Europe that you can see here in the map. And in particular, I want to highlight the 3 larger machines that we have in Europe, which are Lumi in Finland, and Leonardo in Cineca in Italy, and then the brand new Mare Nostrum 5 at PSC in Barcelona. You have also here the last ranking of the top 500 list that was issued a few weeks ago, in which these 3 machines are ranked as the 8th, 9th, and 11th machines. So it's quite good numbers in terms of infrastructure. Then the second pillar is on applications, and here essentially we have centers of excellence and national competence centers, but I want to focus on the centers of excellence. We have now running 12 centers of excellence, and we will see today talks on 4 of these centers of excellence, and in particular ChEESE II, Hidalgo II, EoCoE-III, and then EoCoE-III as well. So you have here the logos, and you will see presentations from these CoEs that in some way or another tackle aspects from natural hazards. And before we start, just to remind you that we will circulate a satisfaction survey, so please help us to giving your feedback after the conclusion of the event. I understand, Ayrton, that we will also send emails to remember this, but you also have here the QR code in case you want to do it now. But I mean, we will circulate this link also after the event. So that's it from my side for the introduction. And even if we are ahead of time, I think that we could start with the first speaker. So we will start with Yasemin Korkusuz from the Binali Yildirim University in Turkey. She's a seismologist, and she's also an assistant professor with experience in earthquake rupture simulations, and in particular for high-risk fault lines in Turkey. She has done also a postdoc and doctoral and master's degree research at the Department of Geophysics at this university, and She will talk about the 3D dynamic earthquake rupture simulations for the potential main Marmara fault earthquake and magnitude 7.8 earthquake. So I think we could start. I will stop sharing and give the floor to Yasemin.
Thank you very much for the introduction. I needed a request to share my screen.
Yes, maybe Ayrton should enable all the
I think now you can see my screen.
Okay. So the floor is yours, Yasemin. I will just, in case, give you some warning after 25 minutes, in case there are questions in the chat. So thank you.
Okay, thank you very much. Hello. At first, I would like to welcome you all. Today, I'm going to talk about our 3D dynamic earthquake rupture simulations in Turkey based on stress heterogeneities on non-planar fault systems. If I give a quick outline, first I'll talk about our simulations for the expected main Marmara fault earthquake, and then I pass to Kahramanmaraş earthquake occurred on the 6th of February 2023 with magnitude 7.8. Then I will mention about what would have happened if the earthquake had initiated on a different segment for the next cycles. If we start with the main Marmara fault earthquake, this study comprises our 15 years research actually, and it consists of numerous data sets. And we generate 3D dynamic earthquake rupture simulations for the expected main Marmara fault event close to Istanbul metropolitan, considering stress heterogeneities. As most of we know, there is a seismic gap in the Sea of Marmara, which is shown by purple ellipse here. And the segments of the main Marmara fault is also shown here. And as we see, the closest points of this segment to the south coast of Istanbul is just 10 kilometers. Therefore, it's significant to generate realistic earthquake scenarios and shake and hazard maps through physics-based approach to protect lives. If we have a quick look at previous research, there are 2 studies done for the expected Marmara event, but in both studies, they used exactly homogeneous initial shear stress distributions. But in the study of OH and Ulrich, they used a boundary integral equation method, while in the study of Gillespie and May, they used finite elements method. And the results are also quite similar. Western initiation of rupture is the worst case. When they initiate the earthquake in the Eastern Marmara, rupture does not propagate effectively. And also in both studies, rupture enters to the Izmit segment. Izmit segment was the segment, is the segment already ruptured during the 1999 Izmit earthquake with a 7.4 earthquake. And also interestingly, there is a jump here. Rupture does not propagate into the Princess Island segment and jumps from Kumburgaz Basin to Izmit segment. Therefore, we decided to generate 3D dynamic earthquake rupture simulations considering stress heterogeneities. We use the shown formulation, which is the multiplication of rigidity, which is globally 32 gigapascal, and slip deficit rate and elapsed time since last large earthquake. In order to identify elapsed time, we used historical earthquake records and turbidity records. For the slip deficit rate, we use data from geodetic studies. And also we considered partial coupling behavior of the central Marmara with the help of repeating earthquake and strain meter studies. And after that, we also calculate normal stress values using recent stress tensor inversion studies. And in this study, here you see the segmentation of the main Marmara fault we used. Our assumptions are that stress is totally released during the last large earthquake for each segment, and Kumburgaz Basin has not been ruptured for the longest time, and Kumburgaz Basin, which is shown by F, is ready to rupture. Here we see the 3 geodetic studies which we use their annual slip rates. We know that the annual slip rate of the North Anatolian fault zone is 20 millimeters per year, but if we focus on the central Marmara, it becomes very small. It can be even 2 millimeters per year. And also from the other studies, we can clearly see the heterogeneity within each segment. Therefore, we select the useful values of these annual slip rates regarding our fracture criteria. After the identification of slip deficit rate, we pass to the elapsed time since last large earthquake. First, we try to plot this map, which shows historical earthquake activity of the Marmara region. Unfortunately, we don't have instrumental data except from 1912 earthquake. Therefore, we don't know the exact locations of these earthquakes, and also we don't know the rupture extensions of these events. Therefore, we cross-check this data with the turbidity records. Turbidity records are taken from the inside of the fault, and they show deposited they show sediments deposited during earthquakes. Therefore, by combining these data sets, we finalize the last cycle of earthquake in the Marmara Sea as seen. In the West, we finalized that the 1912 Ganos earthquakes extended to the east until the western entrance of the central Marmara Basin. When we look at the eastern Marmara, for the Princess Island segment, we couldn't become sure if it last ruptured during 1894 or 1766 events. Therefore, we make our simulation considering both these cases. For the central Marmara, we decided that all segments are last ruptured during 1766 earthquakes. After the identification of initial shear traction distribution, we passed to the calculation of normal stress. Since we assumed that Kumburgaz Basin is ready to rupture, we calculated the absolute value of the normal stress for the Kumburgaz Basin, and then we project this into other segments using this recent local stress tensor inversion studies. And these are the maximum horizontal stress axis distributions. Inward arrow is the direction of the compression which we used for the projection. And here we see our fault geometry in 3D. It is almost similar with the one from Gillespie and May. The only difference is that we remove a 2.4 kilometer long segment for simplicity, but we make tetragonal mesh, and which is increasing gradually with the distance from the fault edge. And we use 200 meter grid size for 100 of seconds, and we model 18 million cells in total for our each model. And for our 256 gigabyte computer, it took around 12 hours for HDF5 outputs. And here is the summary of segmentation of our model. And we decided that the locking depth of the each segment is changing between 10 and 13 kilometer depth. And also annual slip rate is ranging between 9 and 20 millimeter per year. Also here, green circles are the repeating earthquakes, which serve as indicators of partial coupling. Here are our 17 master initial models for the initial shear traction distribution. On the top 5 models on the left side, all segments are totally locked except from Central Marmara and Western High. Central Marmara is 25% coupled, Western Marmara is 75% coupled. And in the top model, we distributed this coupling amount homogeneously, while in the others, we are changing the locking depth of this locked layer. And also here, we distribute asperities heterogeneously. And the difference of these bottom 5 models from the upper is that Western High is tempering up to 8 kilometer depth and totally locked between 8 and 11 kilometer depth. If we look at the 5 scenarios on the right side, the only difference from the lower left ones is that the Central Marmara is 50% locked. If we focus on the last 2 models, all segments are totally coupled. And in the last one, all segments are locked up to 15 kilometer depth. And we repeated these 17 scenarios for this selected 3 possible rupture initiation points, and also for the cases that the Princess Island segment, which is shown by G, could be ruptured during 1894 or 1766 earthquakes. Now I would like to show you the slip distribution result as a result of scenarios. Almost in all scenarios, we observe the largest slip in the Kumburgaz Basin segment, and also we observe high slip in the Princess Island segment. But as we see, if the Princess Island last ruptured during 1894 event, rupture may not enter into this segment. And when we look at the maximum slip at the segment B and C, which were already ruptured during the 1912 Ganos earthquake, it's almost half comparing to the Kumburgaz Basin. This is what we expect to see because the accumulated stress is lower at those segments. If we look at the moment magnitude distribution, it's changing between 6.9 and 7.3 for these 85 scenarios. And here is the slip distribution scenario for the best case. Best case means that's the minimum magnitude scenario. The magnitude is here, here is 6.9. Since the Princess Island was ruptured during 1894, rupture does not enter to this segment. And Central Marmara is heterogeneously loaded, and Western High is tempering, and this scenario is finalizing within around 26 seconds. And if I pass to worst case scenario, this is the displacement distribution. So we are looking at the ground surface. Waves are reaching to the ground surface within around 5 seconds, and the magnitude of this event is around 7.3. Princess Island segment last ruptured during 1766 earthquake, and due to the rupture directivity and geometry of the fault, we observe the largest displacement in the Central Marmara in this case, as you see, instead of Kumburgaz or Princess Island segment. And this scenario is finalized within around 32 seconds. And up until now, I mentioned about our 3D dynamic earthquake scenarios, 85 scenarios, which considered interseismic stress load. Now I would like to introduce you a new scenario. Here we selected a master case, and we wanted to see the stress perturbation effect due to the Ganos earthquake on the west and Izmit earthquake in the east. Therefore, we are pulling these two blocks from two sides and also from the bottom. By fixing the main Marmara fault segment, we are trying to calculate accumulated stress on the main Marmara fault segments. By summing these incoming stress with the interseismic stress accumulation, we make a new scenario. And when we calculate new scenario with the previous one, we observe around 50 centimeter increase in the slip, especially in the central and eastern Marmara. And also we see 0.1 unit increase in the moment magnitude value. Here I would like to show you peak ground velocity maps. On figure A and B, we see the best and worst cases for heterogeneous scenarios. In C and D, we see the, again, best and worst case scenarios for the Princess Island initiation cases. In the figures E and F, we see the best and worst scenarios for fully coupled cases. If we focus on figures G and H, these are for the same scenario. In figure G, we added stress perturbation due to 1912 and 1999 earthquakes, while we lose it in figure G. And if we compare these two figures, we can see the extension in the contours of the PGV values through the Istanbul. And if I summarize this part of my presentation, for the first time in this study, we quantified heterogeneous initial shear stress along the main Marmara fault by considering historical earthquake data, turbidity recourse, and interseismic coupling. And also I want to emphasize that these results are valid if the Ganos fault will not be dynamically triggered. Actually, during our initial scenarios, we could observe that just a few degree rotation in the principal stress axis can lead to dynamic trigger. And we obtained 86 dynamic earthquake rupture simulations in total. One of them incorporates stress perturbations due to Ganos and Izmit earthquakes. And Princess Island segment acts as a barrier for the expected event. Low initial stress is not sufficient to stop rupture penetrating to the west of the central basin. If the most recent rupture of the Princess Island segment occurred in 1894, it's unlikely to be the initiation point of the future earthquake. And the rupture can continue to propagate along the whole Marmara fault, although we use a detailed geometry. And the largest maximum slip can reach up to 6.1 meter, and most of scenarios end up with an earthquake around 7.1 and 7.0, but it can also reach up to 7.3 or 7.4. And PGV values reach around 0.4 millimeter per second at the south coast of Istanbul. And by incorporating the stress effects of the 1912 Ganos and 1999 Izmit earthquake into our master dynamic earthquake simulations, present that PGV contours expand across the both Asian and European sides of Istanbul, corresponding to an earthquake that is 0.1 magnitude larger. From this part of my talk, I would like to mention about our preliminary results for the 6th of February Kahramanmaraş earthquake with magnitude 7.8. Here we see the surface rupture traces of these two earthquakes of Kahramanmaraş earthquake doublets. As most of we know, it's initiated on a splay fault, Narlı splay fault, and then triggered the segments of the East Anatolian fault. Here is the slip distribution derived from a kinematic inversion study. As we see, slip distribution is quite heterogeneous. It's very low at Narlı segment comparing to the East Anatolian fault, and slip is extremely high in the entrance of the north-northeast of the East Anatolian fault, and then it becomes close to zero, which may correspond to this branch. But interestingly, it increased again with a super shear rupture to the Erkenek segment. Also, we know from the observational data is that there is a time delay to the south-southwest propagation of rupture. Therefore, some questions rise, such as how the slip distribution and rupture parameters were affected by the rupture initiation at a splay fault. And did the segments of the East Anatolian fault triggered via dynamically or statically? Why the surface rupture of the earthquake is quite heterogeneous? And all these factors indicate that the investigation of the dynamic propagation of the earthquake rupture along the East Anatolian fault and the stress conditions which explain the rupture propagation patterns for recent earthquakes are essential. Here is our 3D fault geometry for the Kahramanmaraş earthquake. We try to use 200 meter grid size and also 400 meter grid size. The number of cells decreased from 36 million to 7.2 million by increasing the grid size twice. Since both these values give exactly the same waveforms, we continued with the 400 meter grid size. And we used again 256 gigabyte memory, and it took around 30 hours for 200 meter grid size and 7 hours for 400 meter grid size simulations. Here is our initial shear traction distribution, which is based on surface displacement values. It's slightly heterogeneous and not depth dependent. Here, in order to remove numerical stability problems, we put a small gap between the Narlı splay fault and the East Anatolian fault, which does not affect our simulations. Here is the displacement simulation result for the Kahramanmaraş earthquake. As you see, rupture can directly pass from Narlı splay fault to north-northeast of the East Anatolian fault, and we can clearly see the delay to the south-southwest. And we also compared this data with observational data, and we could observe the compatibility. And also due to wide angle and the motion of the East Anatolian Fault and the Narla Fault. This is what we expect to see. It's very easy to propagate from this segment to this segment, but due to acute angle here, also mechanically we don't expect a direct propagation. And from this point of my talk, I will mention about what would have happened if the earthquake had initiated on the East Anatolian Fault. Now I would like to use a totally homogeneous initial stress structure, and 3 of my other initiation points are located on the East Anatolian Fault. If we look at the initiation at Pazarcık segment, we can see that rupture didn't enter into the Narlı segment, and the maximum slip can be 6.4 meters. If we initiate earthquake on Erkenek and or Pütürge, rupture could propagate to the Narlı segment, and the maximum slip can be 7.5 meters, almost 1 meter higher comparing with the Pazarcık initiation. But if we look at the Narlı initiation for exactly the same initial stress distribution, rupture could propagate to all segments, and the maximum slip could be 8.2 meters, which is the highest slip value. Therefore, unfortunately, we could say that this is what happened during the 6th of February Kahramanmaraş earthquake. And if I conclude my presentation, 0.2 kilometer and 1 kilometer separation of the branch from the main fault didn't change rupture properties, and it may be an indicator of that Narlı splay fault might have been totally connected to the East Anatolian Fault or separated by a distance shorter than 2 kilometers before the 2023 earthquake doublets. And arrival times of observational and synthetic data at near field stations coincide well. Large amplitudes of seismograms are consistent with the rupture directivity and largest displacement. Unfortunately, I couldn't put figures related to these. And the figure at the rupture at southwest of the East Anatolian Fault is triggered by static stress load, while the rupture at northeast was triggered by dynamic stress load, and the rupture wouldn't enter into the Narlı splay fault, and the maximum slip would become higher at the north of the Amanos segment if the rupture initiated on the Pazarcık segment, and the rupture would still enter to the Narlı fault if the rupture initiated on the northeast of the East Anatolian Fault. If the Kahramanmaraş earthquake wouldn't have initiated on a splay fault, maximum slip amounts could be smaller, which implies lower damage along the rupture zone, and the dynamic overshoot at the Pazarcık region may be the reason for very high damage. This is the end of my presentation. Thank you for listening.
Thank you very much, Yasemin. Nice presentation. I don't see any question in the chat. Feel free to step in and put questions. If not, I may have a couple. You did not mention which model did you use for the simulations, or maybe
I used finite element model of Pilot. It's USGS software from Brett Agard. It uses regular finite element mesh.
Okay. And you run it in which system, in which machine? Because you did mention about the computing time, but you did not mention whether it runs on CPU, GPUs, and the number of cores or GPUs that were used.
I used 20 cores, 256 gigabyte RAM. Actually, the not simulation, but mesh program requires high CPU actually, but not mainly GPU. I used CPU actually.
Okay. But I mean, this model is able to run on GPUs as well, or not yet?
The simulation part, yes, but the generation of the geometry and the mesh, I need CPU.
Okay, I see. Okay. Thank you.
Thank you. You're welcome.
Questions from the audience. We have plenty of time, so don't be shy. If not, maybe if you could comment also about the velocity model. Maybe you mentioned not this, but which velocity model did you use for the simulation?
For the Marmara, we used a 1D velocity structure, but for the Kahramanmaraş, we used 11-layer velocity structure. So the stability condition was a little bit difficult for the Kahramanmaraş. During our simulations, there was no 3D structure for Marmara, but now new studies are done. So we are planning to also make simulations using a 3D structure. That's why we didn't present any intensity figure, because we also need to update our PGV values maps to pass to intensity.
Okay. Thank you.
Thank you very much.
Okay. Last call for questions. If not, we will move on to the next speaker. Ayrton, even if we are a bit ahead of time, I think we can proceed anyway, no?
Yeah, we can proceed. Mario is already connected, right, Mario?
Okay. So yeah, our next speaker, let me introduce Mario. Mario is Mario Acosta. He's a computational scientist at the Barcelona Supercomputing Center at BSc, and he co-leads the computational Earth Science group, which focuses essentially on HPC applications for Earth system models and also climate digital twin initiatives. And today, Mario will present us the EoCoE-III Center of Excellence. So Mario.
I would just ask for Yasemin to stop sharing your screen, please. Thank you.
Hello, everyone. Hello, Arnau, for the presentation. So nice to see you, actually. First of all, also, thank you for the opportunity to share the work that we are doing in EoCoE. I'm going to share my screen now. Can you see the slides?
Yes, perfectly. Thank you.
Okay. Okay, so yeah, I'm going to start. So in my case, is going to be more a general overview about the activities that we are doing in this other center of excellence. And actually, also the idea is try to connect with all the activities that you are doing, and also some connection with extreme events, this natural hazard, and how actually our work also can be complementary in some aspect to all the activities in which probably the audience and the expertise in this event is also related. So, oops, it's not moving. No, okay. So this is the idea, no? EoCoE-III is focuses in this excellence for simulation of weather and climate. So obviously we are more focused in the weather forecast or the climate prediction for climate studies, no? For example, to create some scenarios for this climate adaptation and some mitigation. But obviously also we are connecting with some extreme events, hydrological, for example, and well, also the data that we are producing in any case is also super important for all these kind of studies. As Arnau was saying, I'm coming from Barcelona Supercomputing Center, but we have a complete department focuses in earth sciences. So the idea behind the expertise that we try to provide is all this environmental modeling, focusing in this weather, climate, and air quality. So now we are close to 200 people. Mainly we are focusing this horizontal program, but also involved in other initiatives as destination apps. And why it's important this high performance computing and this center of excellence EoCoE for weather and climate modeling. So the point is the different studies in which we are involved, mainly for these climate studies, started to gain some complexity in the last year. So when all the simulation starting with the atmosphere and the ocean, as you know, but then we started to include more and more components that must be run in parallel in the supercomputer, including sea ice, carbon cycle, vegetation. So adding more complexity to this name, which is Earth system model, beyond the typical simulation with the atmosphere or the ocean. Additionally, also due to the chaotic nature of these models, is super important also the ensemble approach. So the idea is not only to run one simulation with a prediction, but actually try to perturb some initial data and try to build an ensemble with some range of the solution. So this means also that we multiply the number of experiments that we need to do just to take one prediction. And finally, also, if forecasting maybe could be 10 days or up to 1 month, when we are talking about climate prediction and climate projection, we are talking about run the model and this application up to 100 years, for example. So this means that we are using this supercomputer with different components running in parallel, different experiments doing exactly the same, but in an ensemble, and running during weeks just to make possible this kind of experiments. And the other one, as you can imagine, is the resolution. So actually, the prediction that can be used for these extreme events is also really close and is happening also for the global Earth system model that EasyWays is working. This one is an example coming from Destination Earth using almost 1 kilometer global, in the horizontal, I mean, global simulation. So as you can imagine, the number of features that we can improve using this resolution for the global model, which is closer, or at least is start to be closer to the regional models. The feature that we can produce here in vorticity or also in the cloud physics is improving dramatically with this kind of resolution. And obviously, all this complexity that I was talking before is increasing a lot the computational cost needed for this kind of model. And also why this high performance computing is super important. But now also we are trying to solve another problem, which is try to remove some of the barrier for decision making. So it's not only to run the model in which we are working, and produce some data that the scientists are going to use. The idea, and actually this is also something super important for some mitigation, climate mitigation, or even extreme event mitigation, is try to move or remove this limitation from the scientific result that we are promoting to environmental services that is going to make possible this decision making in a more transparent way. So the idea is try to develop some specific services that can be used for government, for example, at different scales, and try to ensure that all this information that we are producing is accessible in a streaming approach for the different entity that could be make possible all this decision making. And as you can imagine, all these requirements that I was talking before also need a very high computational cost. And this is also why we need all these supercomputers. As you can see below, just increasing the resolution of the model. Here we have an ocean grid for the NEMO model. Just increasing the resolution of the model means that we need to increase the memory, the time that we need to do the simulation, and also the size of the outputs. And as you see, comparing this ORCA-II and the ORCA-36, the differences are quite dramatical, in the computational cost that we need to make this possible. So actually, running this ORCA-36, which is close to the 2-3 kilometers for the global resolution, means that we need for a climate scenario of 50 years, we need almost 80 real days to make possible this kind of simulation. Additionally, this kind of model are not different to the different application that actually you are using. So the idea is try to work in using parallelization for the supercomputer, where we are using domain decomposition, and then there are some MPI, OpenMP communication to make possible to do this simulation with the high resolution. The key point here is the Earth science model are also very complex. For example, you can see here an structural grid for one of the model that we are using in the ocean, FESON. and try to take advantage of the specific hardware that we are going to use is mandatory. No? So we need some optimization techniques to increase this performance on this model. And here is where the work that we are doing in easy ways or just in the European community is super important. Until now, we were coming from the hybrid era. So this means that we have a supercomputer with a lot of CPU cores, and in some cases also the GPU partition, and we were using this domain decomposition and try to exploit the parallelization with MPI, OpenMP, and GPUs. Now we are moving to the subscale era. Actually, Marmara from BSc is a pre-subscale machine, and we have also in Germany the first subscale European Euro-HPC machine, Jupiter. No. The difference between these two, this evolution with the platform is that we are moving from this multi-core, many-core cluster to something more specifically designed from the hardware. So in this case, we are talking about heterogeneous computation and co-design with some fixed accelerators. So in this case, we have something specifically thought to do some work with application that must be co-designed for this hardware. And obviously, this means that we need more complexity and more programmability to make possible this with our scientific codings, which obviously is not trivial. We have some advantages from this new era. No? So obviously, we have new computing elements, more parallelism, more data. The possibility of this data streaming is not only to store something and just wait for a scientist to take the data, but obviously also we need to solve this issue that I was commenting before with the complexity, no? The resolution, more parameters, more ensemble, more components, or just the larger data set, no, that we are introducing to make possible this climate simulation. Usually in the state of the art, we could talk about 3 different ways or approaches to solve these issues with or to make possible the adaptation to the subscale era. In my case, and also easy ways, we are focusing in the modeling and simulation, no, plus the big data or the machine learning. And in this one, what we are doing now and the activities in which we are involved is the adaptation to the Euro-HPC pre-subscale machine. So here we have -5, Lumi, and Leonardo. Then also we are providing support for destination N. So in this case, the high resolution model developed for this digital twin for the climate DT and also the extreme DT. So also we are involved in one of the climate digital twin, the digital twin, focus it in this extreme DT, for example, regional part of Europe. And then also we are start to prepare the models for the medium long time. So in this case, we have co-designed for the adaptation of the RISC-V or the quantum. We are also exploring possibilities with clouding or just continues the work that we have now for the porting in AI, in this case, the TPUs or the GPUs. And as I said before, no, I'm going to focus in easy ways, but also I'm going to connect with destination N and this digital twin. And we have another flagship model connecting to with this, which is Edito, no, which is actually focusing in this European digital twin of the ocean. Easy ways is started in 2015, and now we are in the 3rd phase. No, so the idea is try to build this SSK system in Europe and try to promote this idea about the center of excellence for weather and climate application. In our case, as I said before, no, the idea is try to support all these weather and climate modeling communities to make possible, for example, the IPCC report. No, so we have different modeling centers running the climate models and trying to contribute to the IPCC report that are using later for these climate adaptation plans. We are a consortium of 12 partners around Europe. We are starting in 2023 and we finish as ChEESE also at the end of the 2026. The idea behind the Center of Excellence is try to have some expertise from weather and climate institution, Also for high-performance computing expertise, some vendors, as for example, Atos, or just them also other partners for communication, training, and teaching. The main goals behind EoCoE-III are try to transfer and establish knowledge and technology for efficient and scalable weather and climate simulation, which is connecting to all this information that I was commenting before. But it's not only the model, no? So the models are coming from the different scientific institutions, and EoCoE-III is also trying to develop some specific tools or tasks just coming from this project. So the idea is try to close some common technology gaps, try to provide some of the tools that could be used for this weather and climate institution to make possible something that is impossible just coming from the scientific project. And finally, also, it's super important to serve as a sustainable community hub. So in this case, promoting our training, communication, and dissemination to connect the high-performance computing community with all these weather and climate modeling centers. To make possible all this, we have two pillars. The first one is dedicated to the technical aspect, and here we are working in co-design to support the application for the adaptation to RISC-V processor, to the GPUs. Also, this developing about community tools, and here we have tools to reduce the precision of the variable of the model, to try to do the computational performance evaluation as profiling, no? In this case, of these models, or also domain-specific languages to make possible the adaptation to GPUs in a more automatic and transparent way. And also tackle the data challenge. So in this case, we are talking about the data management, compression, or all the activities needed, no, to ensure that all the output that we are producing is going to take advantage in an efficient way for the scientists or even just general users. Then also we have a pillar just dedicated to the community. So in this case, we have some HPC services that people apply for free in Europe, and we try to serve these services for the community. And then, as I said before, we have training and also capacity building or just community engagement. About the HPC services, as I said before, no, so we have some calls and we offer these services by free. So in this case, we have a catalog with different activities in which we can help to the community. So everyone in Europe can apply, and we try to produce some optimization of the weather and climate application, or also produce some containerization of the model, data compression. We also try to help to make possible the EuroHPC application, optimization of the input-output of the model, adaptation to the infrastructure, so in this case, -5 and Lumi. And well, in general, also, no, to try to prepare this kind of application, maybe for some universities or people with a minor community, to make also possible, no, to exploit and take advantage of the EuroHPC infrastructure. We have been working in different applications, and no, I'm not going to enter in detail, just to mention that, well, there are applications from all Europe, and we are working for probably the most demanded is the porting to the GPUs, coming from a CPU implementation, but also we are working in evaluation tools, as for example, the SMBAL tool, or reducing the precision of the variable of chemistry application for the system model, or also some general optimization for the different model, no, application that can apply for this. Now we are starting to work in a new one, in a new call, but actually we will open a new call in 4 months. And again, no, everyone, independently of the application or domain topic, if this is connecting to weather and climate, can apply to the EoCoE HPC services. Then also we have another service, which is just try to access to our tools. So as I said before, we are developing different tools for containerization, to reduce the precision of the variable, for profiling analysis. And the idea is try to promote all these tools for free, so people can start to use it for the different application and start to work with all this work. And actually, these tools not necessarily are dedicated for weather and climate. So in general, any domain application will have access to this tool, and maybe they can use it. This service is for supporting. So actually, it's not only provide the tool, but also there will be HPC expert from EasyWays that provide some support to ensure that the people applying for this take advantage in an efficient way of the tool that we are developing. Then also we have some training also for free. So we have hackathon, we have summer school. All this information is in a training calendar that you can visit in our EoCoE-III webpage. And if you are interested, you can check this and just register for free. Also, we have some online training courses. For example, there is one in January related with computational profiling analysis with the BSc tools. It's profiling weather and climate application, but actually could be applied for any other domain. Also, we have all the social media. No, in this case, it's pretty similar to ChEESE. So usually we try also to support all of us. And the idea is try to communicate some of the activities that we are doing here. So if you are interested in some way, also you can find more in our social channels. And obviously, also, we are really involved in dissemination and communication activities. So in this case, we try to participate in different workshops. For example, we have a collaboration with Hidalgo, or just to facilitate some of the activities that we are doing. In this kind of workshop, for example, we were exploring with Hidalgo the idea about produce some of the data that we are promoting from our weather models, that can be used for example, for some wildfire application. No? So they have in Hidalgo some wildfire application. And in this case, we will producing some data from IFS for the weather model to make possible some of the execution in this other project. So this is some of the collaboration beyond a presentation in different workshops, that could be possible also between different centers of excellences to promote the participation and collaboration. Then also, I would like to have the opportunity beyond EasyWays to just highlight the support that also we are doing to the digital twins. And I take the opportunity to explain briefly this because actually is very well connected with some of the extreme events that probably you are also interested in, because in the climate digital twin, is use an unprecedented horizontal resolution and in a streaming approach also to support this decision making that I was talking before. But in the extreme digital twin, that probably you know this one, also with increased resolution, the idea is try to address some of the impact of extreme event in more real time. So we have forecast for these extreme hydrological events, or also for some air quality situation. So in this case also, in both actually, we try to anticipate also some of the extreme events to try to take advantage for the energy production or for other use cases that could be useful for the society. And actually, in Destination Earth, we are also developing different use cases. So the idea is try to produce a lot of data with the simulation, but at the same time, we are developing some use cases to prove the potential about the possibilities in Destination Earth. And here we have use cases with the energy, wildfire, hydrology, extreme events, urban environment, air quality, renewable energy. So actually we are working on this from BSc. And all these also could be connecting with activities in which probably you are also interested or involved. And that's all from my side. So just to mention that in EasyWay, we are really active to try to create an ecosystem where I think that all of us should be involved, and try to share the activities in which we are working and try to collaborate also for future projects or just activities. So thanks a lot for the opportunity again, to share this work with you. I don't know if you have any question.
Okay, thank you very much, Mario. Very nice presentations. So again, questions for Mario from the chat or directly from the audience? Ultra, yes.
Yes, very nice talk, Mario. I enjoyed it very much. You talked about a bit about decision making and streaming of results to the impact models. Could you expand a bit more on that? How would that work? Would the impact models, I think this is also meant what you mean by decision making, I think. Would they take up data from previous simulations, or would you run ad hoc simulations if they are requested by certain impact models? And what's the general model here?
Yeah, so just explaining a general overview. So hello, Guntram, also nice to see you. EoCoE is not working directly on this, but we are doing the supporting for destination air. And here is exactly as you say. So from EoCoE, we are working in this ultra high resolution and just promoting the idea of use the infrastructure. The example coming from destination air is about for example, you're talking about this renewable energy. So the idea is try to create some scenarios for 50 years using the 5 kilometer resolution. So in this case, actually, we are doing this now. We are producing different resolution closer to the CMIP configuration and running all these 50-year simulation. Once we have all this data, we are able to evaluate, for example, from the climate DT, no? We are able to say, okay, let's see where we have the capacity factor for the different variable related with the wind. And in this case, no, we can use all this information along these 50 years to try to do some prediction that could be helpful for the wind farm, no? So we are using this capacity factor to evaluate, okay, maybe in the future, the maximum of the wind is going to be really high in the south of France, you know, it could have the possibility to provide advice to some government to produce or to create these aeolical winds in the south of France, and try to take advantage of the renewable energy. Talking more about I don't know, some extreme events also could be used for heat wave, no? So in this case, also, if we are exploring these scenarios and we notice, no, that the temperature or the precipitation is going to be low in some long period during the summer or something like that, also could be used for this climate mitigation, no? With some strategies that could be try to warn government, no, that this is going to happen, and maybe they could have some actions to try to mitigate this possibility in the future. And this is the scope of destination air, actually. So we are working in some use cases as an examples, but the idea is that anyone, different user, can access to the data and try to use this to create more application and just try to use this data for this prediction.
Yeah, thank you.
Okay, thank you. More questions? No, if not, Mario, maybe I have a couple. One is a bit technical and the other is maybe more, let's say, high level. You show a very nice video in one of your early slides on this 1.2 kilometer resolution of IFS and NEMO, I think.
Yeah.
One of the first slides. Do you also have ensemble simulations of the resolution, or this was like a kind of single shot simulation to show the potential of these high resolution models?
Yeah, so in this one that we are using for visualization is not using ensemble.
Okay.
In this case, it's just one simulation. However, the experiment that we are doing for the climate scenarios are using three members.
Mm-hmm. And I mean, obviously you cannot run more ensembles because of all of the limitations that you mentioned, no, storage and time and whatever. So I wonder, do you really think that 3 ensemble members is an added value, or not with respect to one, in the sense that
Well, it's a good question that maybe I don't have.
my question is, let's put it another way. It's not better to just go to a bit higher resolution and run maybe 15 ensemble members rather than increasing the resolution so much, but retaining only 2 or 3 ensemble members, which does not allow you to sample the whole variability. So that was my kind of question in the sense, no?
Yeah. So in this case, what we are doing is try to promote a mixed solution, because this ultra high resolution are going to use up to 3 members, but at the same time also we are running the same configuration in a lower resolution. So we have different resolution. We call the production, the development, and the testing. All of them are going to be run with these 50 years. The testing and the development, which are the 10 kilometers and the 25 kilometers, are using more ensembles. So the idea is also in a scientific way, because also we have Aqua, which is a scientific validation and evaluation tool, which is going to evaluate the performance score of the simulation. And the idea is try to compare all of them to try to evaluate which one is producing we could say the better prediction, and also understand what we are doing with the high resolution comparing to the previous one.
Okay, clear. Thank you. We have one question and also some in the chat. I will start with Anna and then I will go to the chat questions. So Anna.
Thank you. I just would like to ask a bit more clarification of the statement which you said that the disconnection between hardware and software is hampering the expansion of multi-core. And to comment that I completely agree that the future exascale machines will be purpose-built. That's my personal conviction. But would you please elaborate on this disconnection? What do you mean? This
Well,
one,
yes.
yeah, in your slide, yeah. This
yes.
one, yeah.
So the point is, and actually here, we could play with the synthesis. People who are developing the hardware, in some cases, just are playing to be in the top 500 and say, okay, my new machine is going to be in the first top 10. And the idea to make this possible is try to create something that can do some computation very fast. And here we have a lot of many cores which are able to just produce some minor operation. But in this case, we are starting to have a very real disconnection between the hardware, which is focuses in this top 500, and also the software in which we are involved. So one super clear example, -5 and -4. The memory per core, if we are comparing -4 and 5, in the CPU partition, I mean, the memory per core is exactly the same. And as you can imagine, in our model, in the application that we are using, the memory is also super important, no? Because we need to store a lot of information from the grid and try to have more memory for the specific MPI process, no, that we are using. It's also important to ensure, no, that our models are fast enough for the execution that we have to do. However, the vendors in some cases try to disconnect all these limitations that we could have or this need that we have. So it's important to make this new heterogeneous adaptation connecting also the domain application in which we are working, no? And well, this is more or less not what, as I say here. Maybe we cannot do too much from the vendor perspective, and we need to do the adaptation from our side. But at least this is happening, no? And we need an effort from our side, no, to make possible this adaptation.
Thank you very much. I see. Yeah, that's quite understandable. Thank you.
Okay, thank you, Mario. And we have some more questions in the chat. One from Mirta, and she's asking, is there an estimate date when this high resolution data will be available for the community?
This question is...
I assume that, Mirta, maybe you can step in and clarify. Mirta, you are referring to the destination Earth data, no?
Yeah, probably. So this question is everyone is asking for this. So in this case, maybe this question is more for EC and WF and EUMESAT, because at the end, no, they are the who are going to open all this data. The idea was to free all this data in summer this year. This has not happened yet, but my knowledge is that this is going to happen very soon. So we have a data lake with all the information that we are producing, and I know also that all this is going to be shared with the European Commission, the European Commission, now in Christmas. So this is an event, you know, where we are going to officialize that this information is going to be shared. So I'm expecting that at the beginning of 2025, everyone would have access to the data lake, and probably they can start to use the data that we are storing.
Thank you, Mario. Then another question from Piero Lanucara from Cineca. He's asking, is the energy efficiency part of the HPC service portfolio in EasyWays from a software perspective? I mean, are you considering, I don't know, energy efficiency optimizations in your portfolio?
Yeah. So also nice to see you, Piero. Yes. Also, this is part of our HPC service portfolio. We have a couple of applications that are focused on this. We have kernel Turner to do this evaluation, which is in development of EasyWays, and also in collaboration with the Computational Sciences Department at BSc, also working with the EAR, which is also a application that can be used for this, to evaluate all this energy. And obviously, if also talking about the just a compromise, no, between this time and energy to solution. Also, this is something that from a software perspective, also we compromise from the optimization that we are doing in EasyWays.
See no more questions. Maybe one quick one for you. It's about, I mean, of course, EasyWays, it's going to be a decade-long project, no? After this conclusion of EoCoE-III, that's a lot of time, no? And I saw when I was looking at your presentation, a kind of evolution from, let's say, EasyWays 1, which was pretty much focused on porting parts of IFS or NEMO or some other codes that you have, so we're more to EoCoE-III, in which it's more offering services to the community. You know, you show very nice examples of service portfolio. Now, my question is, this evolution, because I mean, this is something that could be exported to other COEs, but to what extent this is detached from your community, in the sense that, for example, in ChEESE, we have like a kind of balance between geoscience community and software engineer, let's say half and half, no? Now, if the role of the COE is just offering services for porting, optimization, and all this, let's say more engineering or software part, which is the role that your community, the role of the scientists of your community playing in the COE? It's something that is, let's say, losing weight in the sense that they are not needed anymore because you are just offering something. And if the answer is yes, then this could be, let's say, exported to other COEs, no? And because the optimization service is something transversal that actually affects all the domains, and you don't need, to what extent, my point is, to what extent the role of the scientists of each specific domain is important in your opinion when you are doing all these services in general?
So actually there were a lot of discussion around this, you know, with the EuroHPC. My opinion is that the scientists and the HPC, but with the expertise in the specific domain application, are super important for the COEs, and we should not detach, no, from what we are doing now. It's true that in destination we have like an extra effort, no, because we provide these services, and we know that the scientific projects are developing the models. But we are doing, or we try to do this extra effort, no? So maintain the communication with the scientific project as destination air, because we are involved with this one. But also we count on some of the most important institutions around Europe which are also developing the model. So we have representation from IFS, from NEMO, from ICON. So the idea is maybe we are not focusing in the development of this model, but the people representing this model are also involved, and we can continue the collaboration through the other activities.
Okay, thank you very much. Okay, I see no more questions. Last chance to ask Mario. No? Okay, thank you very much, Mario, for your presentation.
Thanks to you.
We will go on to next presentation, which is ChEESE. And this is going to be a shared presentation. I will give an introduction to ChEESE, and then Tomaso will do the rest. Just let me introduce Tomaso, because he's the director of the PISA department of INGV, the Istituto Nazionale di Geofisica e Vulcanology in Italy. And well, to introduce Tomaso is difficult in just one single word, but essentially he's been working at least for what concerns ChEESE on the simulation of multi-phase volcanic flows, and he's the developer of one of the flagship codes that we have in ChEESE. No? So I'm going to share now my screen, and I will start with the presentation, and then Tomaso, I will stop sharing and you will take the lead of that, or?
I don't know, maybe, yes, I can share mine, or you can advance the slides as you
Okay, you just say next slide and I can pass the slides for you. Okay. So now a bit introduction to another centers of excellence. We have just seen easy ways, and we are now moving to ChEESE, which is essentially center of excellence in geophysics and of course in geohazards. We are in the second phase, so it means that this project actually started back in 2019. So it's going to be a 8-year project. But in the first phase, we were pretty much smaller in the sense that we tackled just 4 different domains, essentially earthquakes, volcanoes, tsunamis, and magnetohydrodynamics. And now during this second phase, we have enlarged a bit more the scope of the CoE. And in addition to these 4, let's say, domains, we also have now under our umbrella geodynamics and the modeling of glacier-related hazards. No? If I have to describe ChEESE in a nutshell, I would just tell that probably is the only CoE that covers the 3 different approaches that one may have to exascale. That means we have capability computing examples, capacity computing examples, and urgent computing examples. By capability computing, we mean what most of the people would understand by exascale computing. So it's solving very large monolithic problems that we could not solve so far because of the current limitations of the hardware that we have up to date. Capacity computing is a bit of a different beast. And here in this case, what we have is problems that actually are not that large, so problems that can be perfectly solved with the current or even with pre-petascale machines. But we have cases in which we need to solve very large ensembles simulations to account for phenomena like, for example, model data simulation, uncertainty quantification, data inversion, etc. No? Because in many cases in geoscience, we have a lot of uncertainties in the initial conditions, a bit similar to what Mario showed with the climate simulations. But we have a lot of uncertainties also in the initial conditions and boundary conditions of the model. No? So this is why in many cases we need to solve a very large number of ensembles to span all the range of uncertainties that we may have, and then give a kind of probabilistic forecast or prediction. No? And finally, the third pillar is urgent computing, in which we solve the exascale or the pre-exascale machines. Because we have very, very strong and strict time constraints in terms of time to solution. So here we want these machines to solve a problem that we can afford perfectly with the smaller machines, but not with the time constraints that are required during an emergency. We will see some examples about this. The second phase of ChEESE also sustains on 3 pillars. This is essentially something that has been inherited from the first phase of the project. So we have flagship codes, we have what we call pilot demonstrators, and we have what we call simulation cases and services. So we have 11 of these flagship codes. All of them are open source community codes on the different areas that I was mentioning before. Then we have pilot demonstrators, which essentially are workflows that address these different capacity, capability, and urgent computing challenges that we have. And then the simulation cases are, let's say, the materialization of the pilot's demonstration in particular cases and scenarios. And also we are enabling services on different aspects that are quite relevant in terms of geohazards, like, for example, disaster response, early warning systems, and hazard assessment both in the short and in the long term. This is the list of the 11 flagship codes that we have now under the umbrella of ChEESE-2. As you can see, they cover these 6 different domains. Most of the codes were already accelerated when we started ChEESE-2. This is because these codes that you see here already accelerated in the 4th column, they were already under the umbrella of ChEESE-1. So they were accelerated, ported, and optimized during ChEESE-1. And now we are adopting some new codes that were not under the umbrella. Another important aspect for us is the co-designing with vendors, and this is why most of the codes have mini apps. Mini apps are a smaller version of the codes that we use for testing purposes, and that, let's say, are easy to play for the developers, and in particular the vendors. We are co-designing together with 2 big Euro HPC initiatives, like EUPEX and EUPilot, no? So that's for the EPI, the European Processor Initiative, and the development of the RISC-V, or also with EUPEX, the development of new heterogeneous hardware. You have in the last column also the list of pilot demonstrators where these different flagship codes are used. But I also want to stress that all these 11 flagship codes, 11 is not just a number taken by chance, but it reflects the heterogeneity of our area, no? So we have to cover actually a wide range of physical problems and typologies, and this is just to show you how we can, with using these different codes, solve problems of wave propagation. For example, we have other codes that cover multi-physics, computational fluid dynamics, so it's CFD. Others that cover a particular subdomain of CFD, which is geodynamics. We have also one code for modeling of shallow waters, 2.5D for the modeling of tsunamis. And finally, we have one code which covers a general transport equation. So that's an advection diffusion sedimentation equation that can be applied actually to a very, very large number of problems, not only to the atmospheric transport, but also to the transport of many other substances, let's say. In terms of the flagship codes, what we do in ChEESE is to, first of all, to add new model physics. This is done under the umbrella of Work Package 5, which is the one that is farming this new generation of pilot demonstrators. And here, one of the things that we did not do in ChEESE-1 was to couple the different models. So we are developing new physics here and coupling terms. Coupling terms, for example, could be the case of coupling one tsunami model with one earthquake generation model, so that you can model at the same time the occurrence of the earthquake and the tsunami that the earthquake itself triggers, no? Then very important work package that we have in ChEESE is work package number 2, which is the exascale technical challenges in flagship codes. And this work package is doing a lot of, let's say, activities on the codes, some of which are audit driven. It means that we also collaborate with the POP3 Center of Excellence to audit the codes. We did the first audit run at the beginning of the CoE. And then based on the results of the audit, there is, let's say, a portfolio a la carte of possible optimizations that the different code owners can do, no? Such as, for example, fine-tuning on GPU porting, or more single node or multiple node performance. Some require of algorithmic improvements, others have bottlenecks in the fault tolerance or resilience, IO bottlenecks, etc. So there is a range of things that, depending on the results of the audit, the code owners, let's say, can do in collaboration with software engineers, no? So this is a bit similar to what Mario showed with EasyWays, but let's say at an internal level. We are not at that point yet of opening this portfolio of service to members that are not part of the consortium, but it is something that I think it's quite interesting for the future. And then finally, we have a third work packages, which is this co-designing that I was mentioning before with European vendors and technologies. And here we are using the different mini apps to co-design with these vendors. No? The second pillar is the pilot demonstrators. We have 9 pilots, which I repeat, these are essentially workflows which involve the flagship codes and data stream and particular post-process and tailoring of the results for the end users. And these pilots, they had an initial technology readiness level, and then in the last column you have the target value that we have for ChEESE. No? And of course, the pilots per se are meaningless, and we have to materialize the pilots running what we call simulation cases, which is essentially are configuring and setting up these workflows for particular locations and particular scenarios. No? And to be specific, we have 15 of these cases that you have here plotted in the map, most of them in Europe, but we also have simulation cases outside Europe, or even some that are of global scale. And these simulations will produce open data sets, will allow us to enable urgent computing services. And then some of these data sets, the idea is that they are integrated in thematic core services of the European Plate Observing System. So that's EPO. So in particular, for the thematic core service on tsunamis and volcanoes. So this is the list of the simulation cases. I mean, just to see that we are also running or plan to run during ChEESE-2 a lot of simulations, some of which are really what we call scientific run challenges. So these are capability runs which require of full-scale machine execution, let's say. So here you need really, if you run a Mare Nostrum, you need a substantial part of the machine for addressing this. No? Others are capacity, so that's more ensemble-based. And then some of this capacity are also used for this enabling of urgent computing services. All these pilot simulation cases, mini apps, flagship codes, audit results, etc., are available and will be available also at the end of the project in a centralized GitLab repository, together with metadata that is, let's say, consistent with a machine actionable data management plan. So actually, we don't host in this repository all the code, but we have let's say, links to the different repositories. So this is a kind of single entry point for a distributed repository of codes, simulations, and so on and so forth. No? The third pillar is about the services, and I will give now the floor to Tomaso, but just to mention that we have 3 typologies of services. The first one is on urgent computing, and our goal is, and has been since ChEESE-1 actually, the possibility to make available to end users these services through the Euro HPC system. This is not easy for reasons that we can discuss later if you have questions about how to access an urgent computing access mode on the Euro HPC systems. But we are enabling 4 of these services that result from pilot demonstration 1, 4, 5, and 6. Tomaso will talk about this. We also plan to have 2 services integrated as TCSs, as thematic core services in EPOS, in particular the Global Tsunami Hazard Map and the European TEFRA Hazard Map. And then, of course, in collaboration with Castiel, we are working on this CI/CD strategy of our 11 flagship codes on the Euro HPC system. So I will stop here and give the floor to Tomaso, or maybe Tomaso, just if you want.
Okay.
I don't need to stop sharing. I mean, just.
Okay, I will tell you when I want to advance the slides. Thank you, Arnau. Hello, everyone. Thank you for the introduction. And I start from this slide telling that the idea of the services was born in ChEESE-1, and the target for the services are both the scientific community in some sense, and some stakeholders that we have identified. I will talk about that a bit later in further slides. The idea is that there are many services that are useful for the scientific community when we are talking about HPC. Some are devoted to bringing part of the scientific community into HPC, and to demonstrate the the utility of HPC to our community. Because our is a very diverse scientific community, there is the need to demonstrate in some sense. This is why we use the pilot demonstrator, that HPC is useful for science and is useful for society. So we have developed this technological readiness level for ChEESE. That is trying to measure how a product is ready to be used for a broad community, scientific community, but also for stakeholders. And in this sense, we are targeting civil protection agency, governmental agencies, and so on. But okay, today we are talking about natural hazards. Obviously, ChEESE is not only dealing with natural hazards, but natural hazards are an important part of our work. And natural hazards in solid earth sciences have some peculiarities, I would say, that we have tried to address. First of all, the source of the natural hazard is usually very complex and in some sense not directly observed. And this is one of the peculiar difficulties in solid earth. Think about a volcano or the source mechanism of an earthquake, of the coupling between an earthquake and the ocean giving rise to a tsunami. So part of our work, as Arnau said, was devoted to improving the physical description of the source of the natural hazards, because trying to reduce the uncertainty that is intrinsic in this mechanism. And this is the reason why one of the work package in ChEESE-2 was devoted to improving the physics of the models and the multi-scale nature of the models. Of course, the multi-scale nature is characteristic of many Earth system, not only solid Earth. So the source can be very confined, but the effects and the impact can propagate over a range of thousands of kilometers. And this is an additional difficulty for our modeling, because we have to model the source, which is usually very localized, a few hundred of meters for a volcano crater, but the effects can propagate for thousands of kilometers. So this is one of the difficulties of why is needed, HPC is needed in solid earth sciences. The other difficulty is that most of our hazards are, let's say, unpredictable. So far we don't have the capability to predict the occurrence of the hazard of the phenomena, because we don't have direct measurements of the source. We don't have a long time series. And so there is the need of reacting in a quick way when the phenomena occur. And this is the reason for which we put an emphasis and we had this support from EuroHPC in targeting urgent computing. So this is some of the peculiarities that are in our field. So maybe now can go to the next slide. So, for example, some of our pilot demonstrator focus on the physical mechanism of earthquakes. We have heard the first presentation about the physics of the earthquake and the difficulties of modeling the fault rupture and the propagation of the earthquake. In ChEESE-2D, we add to this the geodynamic modeling that creates the faults and the stress before the earthquake, and then we have tasks to improve the physical description of the earthquake. And adding to that, there are groups experiencing techniques of machine learning just to speed up the calculation of the effects of an earthquake to react promptly when an earthquake occurs. As I said, we are not in the position of predicting an earthquake, but there is a very important need to calculate the effects of the earthquake soon after the occurrence of it. Next slide, please. And the coupling of the source in solid earth is also a critical topic. In this case, the coupling of earthquakes and tsunamis, and also in this case, there is the urgency of calculating the potential propagation of a tsunami when an earthquake occurs. In INGV, we run a monitoring room where we keep track of every earthquake occurring in the Mediterranean, and we compute in almost real time the potential for tsunami occurrence. But the simulation of the propagation of the tsunami is still challenging, and for this urgent computing with the HPC is needed. Next slide, please. The same need is for volcanic eruptions. Volcanic eruptions can manifest some precursors that can last months, but again, the exact time and location of an eruption is usually not easy to predict. So there is the need of during at rest phase to both simulate possible scenarios in advance and to be ready for simulating the development of volcanic eruption when the vent opens and the eruption starts. In this case, we use multi-phase flow models to simulate phreatic explosions. We started this work during the crisis in the Vulcano Island in Italy. And we brought this activity into ChEESE to improve the capability to simulate a full eruptive scenarios in a few hours. Next slide. And for staying on volcanoes, as I said, they have very localized effects for small eruptions, but their effects can extend to the stratosphere, and ashes and tephra can be transported by winds in the atmosphere and make trouble with the aviation. And so there is the need when an eruption occurs, and also before the eruption occurs, to predict and to forecast the potential dispersal of tephra in the atmosphere to issue advices for civil aviation. And also in this case, there is the need of producing these results in constrained time frames. Next slide. And this is the part of urgent computing. But as Arnau said, one of the problems that solid Earth has to face is the high uncertainty in the initial conditions, because very often we don't have measurements directly on the source, and the uncertainty is what we call the epistemic uncertainty. So we have to use high performance computing to produce ensemble of scenarios. In this case, the workflow to produce global tsunami hazard maps is represented with all the possible variability in the source. In this case, the possible earthquake sources that can generate tsunami, the possible location, the possible different propagation mechanisms, the inundation mechanism, and so on. All the possible uncertainties combined together and convolved together to produce probabilistic hazard maps. And in ChEESE, we develop workflows to do this on high-performance computing infrastructures for both tsunami in this case. Next slide. And for tephra dispersal for volcanic eruptions, you see here a picture with the possible eruptive volcanoes in Europe, and the idea is to associate to future eruptions probabilities and to build a European tephra hazard map. Next slide, please. Okay, and this is the last part of our commitment in terms of services. ChEESE as what we call an industry and user board. As I said, there are our services are oriented to a scientific community, but also to industry and external stakeholders. In ChEESE-2, we selected a number of committed members and that are listed in this slide. The Italian Civil Protection, Geographic National Institute in Spain, mostly are governmental agencies, but also some centers that serve for civil protection, like the Centro Plinius in Italy and the Buenos Aires VAC that is in charge of the civil aviation in Argentina, and so on and so forth. And with these members, we are trying to organize what we call trials. So maybe you can change the slide, and this will be my last slide. Trials are the way we have identified to assess the impact of the technology developed in ChEESE, to assess the impact of this technology in operational environments. So what is an operational environment? Is the environment in which someone has to make decisions. So pilot demonstrators that I have just presented will be, and those that will achieve high technology readiness level, will develop live trials. And a trial is a live exercise in which the developers of the technology, in our case, the developers of the codes and the scientists, will test the new codes and the new technological solutions and innovation, and will collect the user feedbacks to improve this solution for a real case. The experts that are involved in the trials will help identifying the new scientific challenges, and the external experts will be involved in the creation of knowledge. So all this exercise will be helpful to create new knowledge and new scientific knowledge, but also knowledge that can be helpful to the society. And the stakeholders will focus on the problem in a daily operation. For example, simulate an emergency crisis, a volcanic eruption crisis in the Neapolitan area. And this is useful to initiate the process of assessing solutions. So the trials are a process that culminates in the day of the exercise, but is a process of co-design. So in ChEESE-2, we are trying to do this in a very structured way. And this is something that will be challenged in urgent computing simulation and potentially also in probabilistic hazard assessment tasks. I think I've finished. I don't know if there is anything else. Okay, I leave the stage to Arnau for the conclusions. There is a final slide of conclusions.
Sorry,
Yeah.
I just stop sharing. Well, no, it was essentially a slide to recap on what you already said, no? About the importance of co-designing all these services with end users and to establish clear procedures about who has to do what during an emergency. So prepare in advance, because of course this cannot be done shortly before during the occurrence of an emergency, but that's essentially it. So I think that's it from our side. So feel free, we still have a few minutes for questions. I know coffee time is approaching, but no, okay. Okay, thank you, Tomaso, for that talk. If not, so if we don't have any question, remember that at any time you can always post questions in the chat for the speakers, even if from previous talks. So don't be shy.
Yes, Arnau,
Hi.
I'm Cedric. Can you hear me?
Yes.
Yes, Tomaso. Thank you for your talk. I'm asking the same question I've asked already a couple of times, I think, which is how far are we from urgent computing policies, Europe-wide at least? Are we progressing? What is it like? How does it come?
Good question. I can talk. I don't. I let now responding at a European level. I can respond at at the national level for our experience in Italy. We are not close. We are not close. I think that we are closer from a technological point of view than from a political point of view. Because one of the actions that we have done in the past years in ChEESE-1 and in ChEESE-2 is to, let's say, work to convince that this kind of urgent simulation is useful. So I think that the exercises that we did in ChEESE-1 were very useful from this point of view, because, for example, for volcanoes, which is my field, we demonstrate that in very short time, in that case was less than 3 hours, we were able to identify the critical infrastructure subject to an hypothetical, in that case, eruption at Vesuvius. And the workflow that was developed by our colleagues in Bologna and with Arnau was able to make a full scenario simulation and to chain it with the identification of the roads, pipelines, and things that might have been impacted by volcanic ashes. And this, I think, was a new thing, especially done in 3 hours. The same was done for tsunamis. For tsunamis, the impact is probably the most advanced part of this urgent computing, because for tsunami there is really the time to make a prediction. So obviously the propagation time of a tsunami is very short, but still in our capabilities. Of course, for an earthquake is too fast, or even for an exascale computing. But it's very useful to have a shake map, for example, in the very soon after the occurrence of the earthquake. So I think that technologically we are close. Politically, I think that there is the need to work a bit more.
Yeah, if I may add, it is exactly the same situation at the European level. As Tomaso is saying, we need two things: technology and regulations. For technology, we are there, I would say. Now is a matter of, I don't want to say the word political, but political, let's say, will and establishment of protocols and adoption of integrate this in the Euro HPC infrastructure. This is something that has been on the table of the RIAC and the Euro HPC Council for quite a long time, but it seems that we are almost there forever, but we never reach that, no? So, you know, at least from our side, we are doing our best and we are doing what we have to do. And now there are things that are beyond our control, I would say.
Yeah, I can add that at the European level, one of our partners in IUB is Aristotle. Aristotle is currently a project, but is going to probably to be transformed in a service at the European level. And this is the closest thing to urgent computing that we have, because they have a strict time protocol. So they have to provide an answer to DG ECO, to the European Civil Protection within 3 hours, so that DG ECO can organize, if needed, rescue or whatever emergency service. I don't know. It's something that approaches this idea, but it's not close, as I said.
Okay. Well, as I don't see more questions, we will take a break and we'll reconvene at 4. So enjoy your coffee and see you soon for the next
Thank you.
bunch of talk. Thank you. Okay, welcome back from the coffee break. So let's start again. And I will introduce you our next speaker, who is Carlos Viegas from the Coimbra University in Portugal. Carlos is an assistant professor of the Mechanical Engineering Department, and he's specialized in management and industrial robotics, autonomous robots, and remote sensing, embedded systems, and fire engineering. So he's going to present today IMfire, which is an intelligent management system for wildfires. So Carlos, thank you for your time, for being here, and for introducing us to IMfire. So the floor is yours. You can share screen. And...
Thank you very much.
Thank you.
Good afternoon, everyone. So I'm going to share my screen. I hope you all can see it now.
Yes, perfect.
So today I'm going to present to you IMfire. This is a web-based decision support system that we have developed for wildfire management. So I'm a researcher of the University of Coimbra. We have been working in wildfire research for the past 35 years. And we do not only fundamental research, but also applied research, as you will see later on in this presentation. And we are trying to apply our knowledge about how the fire behaves, how the fire propagates, and leveraging the HPC capabilities to develop these decision support systems to better manage the wildfires. So before we dive into that, let me just give you a little bit of context for the wildfire problem all over the world, actually. So this is a graph of the global temperature anomaly for the past century. And you can see that average temperatures have been steadily increasing in the past years. In fact, last 9 years were the warmest on record, since there is a record of temperatures. And this is a tendency that is global, and it's gonna get worse and worse every year. This other picture shows the global scale of this problem. So this shows the temperature anomaly for all the globe. And as you can see in the first years, like in the beginning of the 20th century, everything was very blue. You have some spots in yellow, some spots orange, which are starting to become problematic. But as we approach these last years and as we enter the 21st century, you can see that the globe is becoming more and more hot, with larger yellow and orange spots. And if we go to the last few years, you will see that this is really problematic. This is scary. And as you can see, throughout the whole region of the globe, we see that everything is getting warmer. Not only the typical regions near the equator, but also other regions, especially in higher latitudes. So this is the impact of this is that not only we are going to have many more fires, but we are going to have fires spread throughout the world. And for you to have another idea of this problem, let me show you here some numbers about the wildfire damage and impact worldwide. So in the last 20 years, we've lost more than 126 million hectares of forested area to fires. This is more than France, Italy, and Germany, the areas of these three countries combined. More than 6.2 million people were affected by wildfires in the past 20 years, with more than 2,400 fatal victims. And each year, we have the emission of 2 gigatons of wildfire carbon globally. So this represents roughly 5% of total global carbon dioxide emissions. So this is a big problem. This is a problem that has the tendency to become even worse. Now I'm going to show you some data about wildfires in the United States. And these lines, the red line represents the area burned, the blue line represents the fire suppression costs, and the bars are the fatalities. As you can see, there's a clear tendency, increasing tendency in the fire suppression costs and area burned in the last years. I'm sorry, this is not updated to this year or last year. This is just to 2018, but it's enough to realize that this is a growing problem. So what can we do to tackle this problem? Because as we can see, we are not doing enough. We need to employ more means. We need to dedicate more research, more tools, technological tools, artificial intelligence tools to help us deal with this. So, but first, we need to understand fundamentally how the fire propagates, how the fire behaves. This is what we have been doing for the past 35 years in the research group of ADAI from the University of Coimbra. So you see here in the video, we show our dedicated fire lab is one of the most advanced fire labs for the research of several aspects of fire behavior. And more recently, we have also been introducing new technologies, robotics, remote sensing, decision support systems, artificial intelligence, and so on to tackle this wildfire problem, not only from a perspective of suppression, but also from a perspective of prevention, post-event analysis, what kind of things can we do in terms of lessons we can learn from what happened, and so on. So this is an overview of my lab that is dedicated to bring technology to this field. And why do we need technology? Because to tackle the challenge of wildfire management, we need to have good planning and good coordination. So we need to take best advantage of available means, because as you've seen, the fire is increasing, the intensity of and the severity of the fires is increasing. So we need to be able to exploit as much as possible the available means that we have. And so if we are able to act in advance as opposed to react, that would be the best case, because then we can direct our means towards the situations where we know that the fire is going to be more dangerous. So for this, we need to have data, and we need to know how to interpret this data, because nowadays everything is collecting data. We have sensors on the ground, we have airborne sensors, we have satellites. There's tons of data that is constantly being gathered about the fire, about the topography, about the fuels, and so on. But we need to be able to process this data and provide useful inputs for being able to do the fire management. So one of the most useful data that we can have when we have to tackle wildfires is not only know in real time the location, intensity, and rate of spread of the fire line, but also being able to predict how the fire is going to propagate. So where the fire is going to be in 1, 2, 3, 4 hours in the future. So that's the role of fire simulators. So basically what fire simulators do, they have information about the topography of the terrain, the cover, the land cover, vegetation that exists, the wind speed and direction, moisture content of the fuels, and a lot of other parameters. And they use these parameters to employ advanced fire spread models to estimate how the fire is going to propagate, so that we can know in advance when the fire is going to reach a certain population or a certain critical infrastructure. So we can have do some actions in advance and prevent situations such as this one, which I'm showing you now. This was a fire that occurred this year in Portugal in September. And what happened was we were able to detect the fire very far away from the highway, but soon the fire propagated towards the highway. No one was expecting that, but we really had a situation with very strong winds. And so the fire was able to propagate very fast towards the highway, and the management entities were not able to close the highway in time. So what you see here is a lot of people that got trapped in this highway, surrounded by fire. And luckily for the person that shot this video, nothing happened, but serious consequences could have happened from this occasion. So we need to prevent this, and we need to be able to detect the fire, and not only detect the fire, but also being able to predict where the fire is going to be in the future, so that we can close the roads, or we can evacuate a settlement, a village, or something. So this is what we are actually developing within the IMfire. IMfire was a research project, a national research project that is now also being used within an European project that we have called Fire Risk. To basically, what you see here on the right is an image of our system. So, and you see the expected fire propagation from the initial ignition that is showing on the blue dot in the center. So what this simulator does is it simulates fire spread and behavior coupled with atmospheric changes for a local set of parameters, including topography, vegetation, and weather. It also simulates the fire-atmosphere coupling and also the smoke generation and concentration. It uses AI for fine-tuning the parameters. And one of the things that we consider that is very important is to have the results fast enough so that they can be used in an operational context. So we are talking about having results and simulation times below 2 minutes. How everything works, we start with the input data. We gather some parameters from our database, including the terrain, the topography, the slope, the elevation maps, the fuel maps as well. And we can gather some information in real time from sensors on the ground or from the authorities, such as the fire ignition time and coordinates, the local wind speed and direction. So these are parameters that we can fetch in real time from several available sources. And then we can also calculate or fetch other parameters such as fuel moisture content and other parameters. So all these parameters, then they enter these models for fire, wind, and smoke and fuel moisture content. And then we produce the results, which include not only the fire rate of spread, but also the fire line intensity, the flame height, the wind map, smoke generation, smoke dispersion, and concentration. Of course, these results might not faithfully reproduce what is happening in reality. So we have here a closed loop mechanism using genetic algorithms, which I'm going to explain to you a little bit more later, that creates this closed loop and compares the results of the simulations with what is happening in real time, and then comes up with a set of parameters that are better suited to produce more faithful simulations. So the basic model that we are using for fire spread is the Rupture model. This is a model that was, this is an empirics model that was published in 1972, so it's more than 50 years old, but it's still one of the most used models for prediction of the fire rate of spread, meaning how fast the fire propagates. We use this velocity of the fire line to then calculate the time that it takes for the fire to propagate from one cell to another. So basically, we divide our calculation domain in millions of cells, 25 by 25 meters, or we can even go higher in terms of the resolution. And each cell has certain parameters considering the wind velocity and the direction, the fuels, the slope, and so on. And so basically what we are doing is propagating the fire from one cell to the other. Of course, we know that surface, the fire model of Rupture is very good for predicting fire spread, but it only counts for surface fires. So it does not take into consideration when the fire progresses from the surface to the trees, to the canopies, or it does also not take into account the spot fires. So basically fire projections that carry the fire many kilometers ahead of the actual fire line and can potentially create more fires. And so what we are doing is we are implementing more models into our simulator so that we are able to predict all or most of the fire phenomena that we are witnessing nowadays. And these are not all the models that we or all the fire phenomena that we are witnessing. There are also some what we call extreme fire behavior, which is becoming more and more frequent in the last few years. And this is actually the fire behavior that is more dangerous because it results in very, very high rates of spread of the fire line, very high intensity fire lines. So people getting trapped, they are not expecting the fire to behave like this, and then they get entrapped, and this often results in fatalities. So it is very important for us to be able to reproduce this kind of phenomena with our models. And here on the right, I can show you two videos which represent quite well this effect, this phenomena of eruptive fire behavior. So what you see there is a junction fire. So basically two fire lines that make a V line. And what you will see is that the fire is going to propagate much, much faster in the center of these two lines. And this is an effect that is not reproducible by the Rotterdam model. So this is why we need to constantly update our models and improve them. Of course, wind plays a huge role in the fire propagation. So it is very important to be able to calculate three-dimensional wind maps and also determine the interaction between fire and atmosphere, because we know that, of course, the wind influences how the fire behaves, but we also know that the fire is able to change the atmosphere through the buoyancy effects. And so what we have here is that the stability of the atmosphere is broken, and we can actually have many fire-driven changes in the atmosphere that are going to play a huge role in how the fire is going to behave. So it's very important to have models that are able to predict these effects. And of course, the smoke. The smoke is also important because it's one of the key aspects when it comes to the health and safety of firefighters. So we don't want our firefighters to be fighting the fire in areas which are with very high density of the smoke because of the pollutants, because of the reduction in the visibility. And this is important not only for fire suppression efforts on the ground, but especially important in aerial firefighting. And so our simulator is also able to generate a 3D map of the smoke concentration in the area. And of course, the question that you all ask is how accurate are these models and how they compare against real data, like real fires or prescribed burnings and so on. So this is a very important aspect for us. Of course, when we make fire predictions, we want them to be as accurate as possible because we want them to be useful for the operatives and for that to help them in decision-making process. And so I'm going to show you now some results in which we compare our simulations against real data. This is an example of some experiments that we did. Actually, going back to this previous slide, this is some prescribed burnings that we do each year, in which we use these large-scale experiments to validate our smoke and fire models. And this is the result of one of those experiments. So basically, we simulated the smoke plume in these experiments, and then we compared against the measured concentration of the pollutants, and we found out that the results, some of them are a bit out of the range of the simulations, but of course this is something that we are constantly improving. And actually these results are not updated, they already have 1 year. I know that the results have improved a lot more in the last year. This is the result of a simulation of a real fire. So here we are comparing the simulation in gray with the real fire in red. And what we see is that our simulations tend to overestimate the fire spread. And this is a behavior that is common to almost every fire simulator. So they tend to overestimate the fire spread, and this can be due to several reasons: incomplete models, no account for suppression actions, inaccurate input data, and so on. However, this is a comfortable situation for us because we prefer to overestimate the fire spread than to actually say that it's not going to be that serious and then the fire is going to be much more serious than we actually initially thought. And so, however, of course, we want to improve our simulations as much as possible. So this is why we are using genetic algorithms to make this improvement. Here is some graphs describing our methodology for using genetic algorithms to improve our prediction. So basically, what we are doing is if we have access to data about the actual fire perimeter in real time, we are able to cross this information with the simulations that we did previously. And then what we are going to do is we are going to generate dozens of simulations in parallel with small variations in our parameters. And we are going to find the optimal set of parameters that deems the most faithful results to what is actually happening. And then we use these parameters for the next simulations. So this methodology was applied to some field experiments, and we were able to increase our accuracy by 40% just by fine-tuning just 2 parameters in our simulator. So this is ongoing work. We intend to actually apply this methodology to many more parameters and further increase the accuracy of our simulator. Of course, this means that we need a lot of resources, and this is why high-performance computing, artificial intelligence is important, because we need to run dozens of simulations in parallel, and so we need to employ these mechanisms to help us get these results in a fast manner. Here I'm going to show you some examples, some use cases of our simulator, which was used not only in the Fire Risk project, but also in 2 national projects, Firefront and the Eye in the Sky. In these 2 projects, we used airborne sensors to detect and monitor the fire progression and sending this information in real time to our simulator. So in the case of the Firefront, we were using unmanned aircraft. And in the case of the Eye in the Sky, we were using high altitude weather balloons with sensors that would detect the fire ignitions and also monitor how the fire was spreading. So we developed an API. Now our system is already working and deployed. It has an API for providing simulations to people or to institutions that already have their own decision support tools, and they just want the components of the fire simulations. So this is the case of REN. REN is the Portuguese company responsible for the management of the power for electricity and gas infrastructure. So for you to have an idea, they have more than 10,000 kilometers of electric and gas lines spread all over the country, and 66% of them are located in forested areas. So each year they have a lot of fires threatening the infrastructure, and so they together with us we started this project Replant, and now it's another bigger project, Transform, in which we are using cameras to detect the fire, and then we are sending these coordinates to our API, and this API receives the coordinates and automatically gives back the results of the fire simulation. So as you can see here, this is the system running, and you see that we have produced the fire perimeter, and then we can cross these 5 perimeters with the lines, so gas and power lines, and we can know where the fire is expected to impact the lines, where and when the fire is expected to impact the lines. Everything that you see here is running 24/7 without the intervention of a single person. So the fire detection, sending the coordinates to us and producing these results and sending out the alerts, everything is done automatically. As for future developments, we intend to use these tools to make a decision support system for fire suppression, firefighting, taking into consideration the means available on site, and also leveraging satellite data, because this is something that is nowadays being more and more used. Nowadays, we have access to near real-time satellite data, and so we are able to detect the fire, we are able to follow the fire in time. And so coupling this with the fire models, with the AI, and with the information about which firefighting assets are available and where are they, we are able to compute dozens of scenarios and find out which are the scenarios that will deem the best results in terms of fire suppression strategies. And so this is what we are currently working on right now. And to conclude, wildfires are really a global scale problem. I like to show this graphic here on the left. This is an image that was an animation that was made from satellite data throughout the year of 2007, and shows all the fires that occur all around the world throughout the year. And so this is good for you to have an idea of the global scale of this problem. So larger fires are likely to occur with increasing frequency in the future, and this context demands for novel tools to aid in the fire management. So we need to couple existing tools, existing fire behaviors, fire behavior models with AI, with HPC, in order to deem useful results to aid in the event management, in the wildfire management. And this is a list of our most recent publications in the last 4 years. And this is it from my side. Thank you very much.
Thank you very much, Carlos. Super interesting talk. I think we have time for 1 or 2 quick questions from the audience. No? Okay, if not, maybe I have one with more curiosity, no? Because you show that actually what you're running is a suite of models that are concatenated, no? So you have a fire meteorological processor, then a fire propagation, a smoke propagation, so it's a chain of different models. So my question is whether if you have some bottlenecks in this, in the sense that they have to run serial, I understand, so, or they run at the same time, and I understand that they maybe have different performance, different capabilities. Some might have some legacy, so they are not, let's say, at the same level of performance. And if some of them might be a bottleneck in terms of time to solution, no? If you have to run the workflow with all this synchronized.
Definitely. Thank you very much for your question, Arnau. Yes, that is true. We need to run them in sequence. So first we start by calculating the wind maps, then we run the fire, and then of course we need to go and at a certain number of iterations we need to run again the wind simulation, because we are simulating the coupling between fire and atmosphere, and the smoke is the last thing in the chain. So basically we calculate the smoke once we have an information about how the fire progressed. And actually our bottleneck is the wind map simulator. That's the more complex one, because it's a 3-dimensional model with a high resolution, not only temporal but also spatial resolution. And so that's the one that takes more time. We are exploring several different models. We have been dedicating a lot of effort into making these models more efficient, but that's currently the bottleneck in our chain of events right now.
Thank you. I mean, to me, it was very interesting because in our community, we have sometimes similar problem with the lava flows, no? We have extensive lava flows, which if they occur in, let's say, vegetated zones, they actually have a strong influence on the local wind field, which in turn affects the meteo, etc. No? So it's something that we saw, for example, in La Palma. Also, it's nice to see that different communities are facing similar problems. So thank you. Tomaso?
Thank you, Carlos. Very, very interesting topic, very urgent thing to address. I have a curiosity about, you have mentioned in some slides the Navier-Stokes models for fires. There was mention, so I probably missed, but how accurate is this kind of modeling, 3D time-dependent modeling, in terms of modeling of the source, combustion, and all the chemical? I don't know. I just wonder if you can go more in detail in this point.
Yes, about that, the specific part of the wind and the smoke, this is actually done by, it was not a work that was done by us, it was done by partners in the project. So I cannot answer in detail about the accuracy of this. I know that they are constantly improving this, that we have achieved. Actually, we are working together in a new project and which is the smoke.
Yeah, maybe I misunderstood that there is also some ideas of Navier-Stokes modeling of the fire itself, of the combustion process. I mean,
so yeah, this is the smoke storm project in which we are working with them, the University of Aveiro, and they are responsible for all the modeling of the smoke. About the wind, that's where we apply the Navier-Stokes solvers to generate this coupling between the fire and the atmosphere. How accurate this is, honestly, I don't have those metrics. I cannot answer that. But yeah, we know that using this deems better results and more faithful results about the fire progression than not using this, because there are a lot of fire simulators that do not contemplate the coupling between fire and atmosphere. So we know that this is an important improvement. Now, about the scale of this, I don't have the data now to answer you. Sorry.
And is anything in the literature concerning really modeling the not just the smoke, but the fire itself with full 3D equations?
Definitely, yes. There's this fire modeling, as I've mentioned, has been a hot topic of fire research for the past 60, 70 years. So yeah, there's a tons of models, both 2D, both 3D, that for fire, for smoke, for wind. So yeah, there's a lot of data about this.
Yes, I agree with that. Now there is lots of crossing and intersections with what we do indeed in terms of high temperatures, dynamics, and interaction of these high temperature flows and reactive flows with the atmosphere. Thank you.
Welcome. Thank you.
We're running out of time, but a quick question, if you can answer to Roberto. Ciao, Roberto. He's asking about which programming languages you are using. If you can answer very quickly, please.
Sure. We started by using Fortran, and then right now we are doing everything. We are passing everything to Python. So because all the platforms and all the modules are being developed in Python. So initially the fire spread model was done in Fortran, but then now we are employing Python.
Okay. Thank you. So let's move on. Thank you very much, Carlos. Very interesting. So let's move on to our next speaker. It's Alessandro Paciaroni from the Lisbon Council in Belgium. Ciao, Alessandro.
Hi.
He's a digital governance expert working on helping the public sector with ethical issues and implications from emerging technologies, I understand. So thank you, Alessandro, the floor is yours.
Yes, thank you. I'm just updating the setting because it was not
In the interim, Carlos, I take the opportunity to ask you about this project. Is this project still ongoing, or what you show it's already finished?
I'm sorry, was this question for me?
Yes, just
So, yeah,
yes.
the IMfire project is finished, but we are now working in the fire risk project, which is going to finish next year. And we are also already making some preparations for new projects to give continuity to this effort.
Okay, thank you.
Thank you.
You can try now, Alessandro, maybe.
yes. And now you should be able to see it, right?
Perfect.
Yes.
Okay, great.
Not displaying in full mode yet, but
Yes. So
okay.
thank you for inviting me. And as you were anticipating, I work in digital governance and digital transformation at the Lisbon Council. The Lisbon Council is a non-partisan and non-profit think tank based in Brussels that works mostly in research projects funded by the European Union and specifically in policy impact. So what we aim to do is always bring the results of the project to an impact across the whole European Union and, ideally on a whole societal level, so beyond the EU. Today I'm going to be addressing how we do this in TEMA and what TEMA is and aims to achieve. Very quickly here you can see that TEMA is a Horizon Research and Innovation project, and that we are midway because the project started in 2022 and will be finishing in 2026. Talking about the significance of this project, we have seen, sadly, a dramatic increase in terms of disaster, mostly what we usually call natural disasters that are not so natural in the cause, meaning that they are actually deriving from man-made interventions in terms of pollution and disruption of the ecosystems and the environment. This brought us to a climate crisis, and we are seeing the effects of this climate crisis in an increasing number of regions and in ways that are more and more deadly for the entire ecosystem. This has been tackled in many ways, mostly with the innovation, with the use of new technologies and the development of new services. Now, while these services and these new technologies have been useful for coping with disasters, their adoption and their widespread use has been quite lagging behind. Why is this? This is because of a number of reasons. They are mostly summarized in this slide. On one hand, we have the issue of trustworthiness of information. So the fact that some services are developed based on the use of certain data does not guarantee the fact that the end user eventually consider those data as trustworthy and that solution as trustworthy. Another issue has been the one of transferability. Solutions developed in a specific context have not necessarily been able to be used in a different context. This is for a number of reasons, which we can summarize with interoperability. So it could be something on the semantic level, could be something, so what the data is, what it means, and so on. Could be something on the technology level, or many times it's also something on how processes are conducted in a certain organization and how laws are written in different areas. And then there is also an issue in terms of the effective development of advanced solutions. So I'm not just claiming here that the solutions already exist and they are just not adopted. There's also, of course, issues related to whether these solutions are actually effective in practice or not. This, for example, on a more technical level, relates to issues of connectivity and of computational resources. In terms of the goals, so I presented now the significance of the project, why are we here, and now I am going to address what are we aiming to do. As you can read in this slide, TEMA aims to develop beyond state-of-the-art technologies for facilitating natural disaster management. This is quite generic, but at the same time, it's the best way of approaching the project, because what we will see in the next slide, which is a bit more detailed, is actually you can reconduct it to this overall vision, which is the one of improving the overall natural disaster management suite of services and technologies, if you will. Going a bit more into detail in the specific objectives, you can summarize them in 3. One is improving services, improving natural disaster management services. This is very much related to the end users. Another one is improving modeling. This is related to the actual phenomenon modeling that is used for situational awareness. So what we also saw in the previous presentations, how wildfires are modeled, and whether this is done in real time, quasi-real time, and so on. And third, improving the operations. This relates to the infrastructure. So this relates mostly to the use of the edge-to-cloud continuum and the distribution of the use of resources, computational resources, and so on, for the rest of the solution to be able to run properly and to eventually, again, deliver the improved models to the end users, so that the natural disaster management services are effectively improved in practice for the end users. Now, looking at the concept, you see on the left-hand side all the data sources that are used within TEMA. From there, you can see that TEMA gathers data from an heterogeneous number of and type of sources. This feeds into the project in 2 ways. One, the modeling and the phenomenon modeling, and the other one is the analytics. Going from the phenomenon modeling, you see that there is on the right hand side an extended reality-based interactive visualization and response planning and recommendation. This feeds into the pilot trials. Modeling and the phenomenon modeling is, of course, tightly related with analytics. So this is at the bottom of the slide. In this case, analytics is very much related to how information, how all the heterogeneous data sources undergoes the information fusion and is able to be used by the improved phenomenon modeling. Again, this feeds into the pilot trials. The pilot trials goes into an iterative cycle together with the case studies. So the pilot trials is the final testing of the TEMA solution. The case studies are based on historical data. We'll also look at this in a moment, and they are used to train the model. And as mentioned before, this is done in an iterative way. Now, going to the applications, we have 4 pilots that are divided in here in 2 slides. One replicates the Central European regional floods and the one that happened in Bavaria a few years ago. Another one simulates and replicates the flash floods, and in this case, the Mediterranean flash floods. In this case, we use a case in Greece as an example. The third one replicates the Mediterranean forest fires, specifically the one in Monteferro in Sardinia. And then the fourth one replicates the forest fires that are more typical in the Nordic area. And in this case is the one in the Kayani area. So in all these 4 pilots, what will happen is that historical data will be used, and I'm moving back to this slide. Historical data will be used to train the model, and the results will be then applied for the case studies. For the pilot trials. And in this case, we are currently planning, even though it's not fully confirmed, to run them through exercises like MODEX. So the idea is that we will be able to test them in real life, although at the moment it's not 100% clear how this will be done. Now, for the impact of the solution, I actually included this slide for future reference because it's pretty much what I have been summarizing so far. So the idea is that overall, on a large scale, the objective is to scale up the European capacity for extreme data analytics. On a more detailed manner, the idea is to improve phenomenon modeling and the response planning. This is, of course, also specified in a series of more detailed KPIs that here you see written down as the reduction of emergency response times, improvement of decision making, and so on. Overall, I think the most relevant for the innovation, and perhaps also going to what in my understanding is the objective of today's workshop, to understand how high performance computing services are used to tackle geohazard. The idea of the project is to open a new market segment via an envisioned extreme analytics as a service. So in this case, what TEMA aims to do is to set up the scene to conduct natural disaster management as a service. And to do this, and this brings me to the final slides of the presentation, we go to the implementation of the innovation. What I am going to address in these final slides is let's say, very specific understanding of this ecosystem. So I'm talking about artificial intelligence, high performance computing, innovation, and emergency management in this specific context, which is the European Union and emergency services. What we saw is that there are 2 critical points here. One is the innovation in disaster response, and another one is innovation in the overall community. What I mean by this distinction is that innovation in disaster response is mostly looking at innovation in the public sector, in civil protection, Red Cross, and so on, while innovation in the community is looking at the broader ecosystem. So in the case of innovation in disaster response, we see that we have 3 main points that we should be looking at. One is the human side of innovation. Another one is the capacity and capability to innovate. And the third one is interoperability and collaborative governance. For the human side of innovation, we see that there is, luckily right now, quite a high awareness in terms of the need for upskilling and reskilling of public servants and I would say society altogether. On the other hand, we often see that we are a little bit moving in the dark because there are excellent examples in terms of frameworks that could be used. However, there's not so much action that is being taken. This is, of course, one could find the reason in this in the fact that there is an issue in terms of competencies. The European Union can only coordinate when it comes to education, while it's up to the member states to actually implement policies and action plans. However, perhaps, and this is also a bridge between the disaster response and the world community, we could do something as a community to ensure that there is an effective uptake of this innovation and the skills. For capacity and capability, well, capacity, I think it's something that everyone in this webinar has been dealing with for quite much. In terms of capabilities, we see that the new technological landscape is much more complex than it used to be. Before, you would mostly procure IT for a very specific function. Say, manage documents, and you would buy some software that would allow you to do that, or you would do that through maybe Google Drive. Today, especially in this field where we have a fast evolving landscape made of drones, AI, blockchain, cloud, and so on and so forth, it's much more complicated to understand it. And it's much more complicated to understand what's going to work and what is not going to work. So we need to look at what do public sector organizations need to be doing today to win in technology and to win in innovation. And let me just clarify that here, winning in innovation, it also means saving lives. There are, again, resources on this. What I am calling for in this at this point is action and is a discussion on these topics. And then very briefly on interoperability and collaborative governance, we see the European Union putting forth certain actions in this sense in terms of the Interoperable Europe Act and so on. At the same time, for me personally, it was quite surprising to see how behind is interoperability in a field like emergency management and disaster response. I started working on this specific field. I come from another field just a few years ago, and I thought we were much more advanced. When it comes to the innovation in the community, one point I think it's quite clear today is artificial intelligence for all. This does not look at the whole society, but it looks at all the organizations, all the actors in the ecosystem. We know that developing certain models is resource intensive. So who has these resources? Who is developing these resources? What does it mean for another organization, a smaller one, to access these models, to access these resources? And together with this, again, the issue of interoperability platforms and the service ecosystem. There is, in my opinion, a trade-off here between giving access giving a distributed access to artificial intelligence and computational resources and concentrating this access. Of course, if you concentrate the access, you have perhaps larger scale and meaning more resources allocated to one actor that can develop things at a bigger scale. At the same time, you may be losing in terms of ideas that, for example, can be found only by giving this access to a widespread number of actors that can all of them experiment and try things out. Maybe the point of this presentation was to give answers, but I am actually raising some questions. But I hope that these are very useful for our Q&A right now or for later. Of course, there are also a little bit provocative questions, but here I took AI as an example, but it mostly relates to innovating in emergency services and in disaster response. If you ask me, these are some questions, perhaps the most important ones that we should be asking ourselves in terms of innovating in this field and in terms of innovating with this type of technologies. And then finally, again, looking a bit more at the ecosystem and at the community altogether, another small set of questions that we should be addressing seriously, because we are already at a critical point in the climate crisis. There's a lot of promising technologies and initiatives, but are they really having this big impact, or can they have more impact? This is a final slide on the consortium, and this concludes my presentation. Thank you for the attention.
Thank you, Alessandro. Questions for Alessandro? Maybe I have one, because of course about AI, no, that you were mentioning. I think that access to AI is not a problem, or it's not going to be a problem. I mean, there are lots of repos already and hubs with AI models posted there. But my question was more on if you are tackling in TEMA fairness of AI models and things like reproducibility, provenance, and so on, because there's something that we are also worrying about, in particularly using AI models for decision making and during natural hazard may also have liability implications. So I think that we have to do an effort for making it as fair as possible and as reproducible as possible, no? So I was wondering if you are tackling also this theme or not.
To some extent, in the sense that we are developing, the Lisbon Council is actually in this task, is leading this task. We are developing a framework that is meant to support these type of organizations. So again, organizations that are involved in natural disaster management and emergency response, to use technology according and in line with the mission and the values of that organization. Now, this obviously it's a very broad description of the task. What we mean by this is that we are trying to give, but this is a work in progress, a very specific set of guidelines, recommendations, good practices. We are still configuring the final shape of this task on that are meant to help these organizations and eventually the people working there to do a little bit what I mentioned here in the capacity and capability. So to understand how technology works, what are the possibilities, what are the different challenges, what is it needed to align it with the goals of a certain organization, and so on. A quick, very concrete example on this. During one workshop, someone from the Red Cross mentioned, we were talking about privacy and ethics, and someone from the Red Cross mentioned that while we all agree that we would like no personal data to be collected in these cases, especially because it can show people in distress and in some sensitive situations, there's also a case in point to say that we actually would like to have to be able to recognize a person in, for example, drone images, if this person lost their lives, and if these images can be the only way in which we can give an answer to their families in terms of what happened to this person. If, for instance, obviously I'm talking about the very specific case in which there's a missing body and so on, which maybe seem like a very specific, very dramatic case, but in these situations, it's actually more the norm than the exception. So we are addressing this in this way. Just to clarify something on the access to AI, maybe I didn't explain what I meant by that clearly. What we see is not that there is what we see, or what I'm raising here as a point for discussion is not that there won't be access to AI, that it won't be possible, but to be aware of who has it and who doesn't. And this is not necessarily in the sense of someone gatekeeping the access to AI, but it's also a matter of resources and capabilities, in the sense that even though the local government or the region X has technically the possibility of accessing AI through AI factories, through supercomputing centers like the one in Barcelona and so on, will they actually be able to put this in practice? Do they actually have the necessary level of data maturity to do that, or they don't? So I think this is a critical point, but of course, this is also like the view that we have in this project. Maybe we were just unlucky with the regions.
Okay, thank you. I see no more questions, so I think we should move on.
Yeah, I do have one.
Okay. Very quickly.
Yes, sure, very quickly. Cedric from BSc. About following up on your comments on ethics, have you identified any general ethical issue at societal level in NDM, natural disaster management, in relation or not with AI?
What do you mean by societal level? Like, you mean just overall, if we have identified some common themes?
At societal level, I mean, questions of bias, for instance, associated with the use of AI in general in such a context as NDM, or not. It could be no.
No, yeah, not really. At this stage, we have not really. They mostly refer to two things. One, privacy. Well, actually, yeah, only one, privacy. It's mostly the main concern and the main issue. Although, to be fair, it is ethical. It's not so much related to regulation, because the GDPR has the force majeure clause, which allows the use of personal data in case of a force majeure, and a disaster is one of them. So it's very much more related to ethics and to the risk of non-compliance, meaning that from what I see, or what we see, especially in the public sector, there's a high risk aversion towards non-compliance with the GDPR, which most of the times prevents action, meaning it stops public servants from trying to innovate and trying to experiment with data, because they are under the assumption that this may infringe the GDPR.
Okay, clear. Thank you, Alessandro. Thank you very much.
Thank you.
Okay, so let's move on for the sake of time to the next speaker. He's Daniel Caviedes from the Jülich Supercomputing Center in Germany. Daniel is a computational, hi Daniel, a computational hydrologist, and he's the team leader of the simulation data lab for terrestrial systems at Jülich. And today he will talk about EoCoE-III, which is the energy-oriented center of excellence for exascale HPC applications. So Daniel, thank you. The floor is yours.
Thanks, Arnau. I trust you can hear me now. I tried to speak earlier
Yeah,
and it didn't work out.
Yes, we do. Very well.
Very good. Okay, so thanks for the invitation to participate on this quite interesting workshop. So what I want to tell you briefly today is it's a mix of things. On the one side, it has to do with the work that we do here in Jülich that intersects with water-related hazards. It's not exclusively based on, let's say, natural hazards in the typical way that we understand it, like disaster management. But it intersects strongly with it. And also the work that we're doing in EoCoE-III, that's the energy-oriented center of excellence. And as its name implies, it's, centered around energy. But because there is this intersection between energy and water, we have this interesting interaction. So I hope I can convey what the interaction is and how the work that we're doing in EoCoE currently, which is strongly HPC oriented, is benefiting the work that we're doing in terms of water and natural hazards. I would very much like to stress that most of the work that I'm going to show is not my own. It's actually, a compilation of the work of many colleagues here in Jülich who work on hydrological simulation, and of course, a collection of the work that we are collaborating in EoCoE with our colleagues around Europe. So hopefully I will do them justice. I would like to start by very briefly telling you about EoCoE. So it's actually EoCoE-III. So it's the third incarnation of this project. You can get a broad idea of what the consortium is, and there's different sides to the project, which I will not cover in full. I will just cover essentially the part that relates to the water sector. There's a core idea in EoCoE, which is perhaps not the same approach that other centers of excellence have taken, which is we fundamentally want to avoid the idea of improving and modernizing our codes through working with dwarfs or mini apps or toy problems, however you may want to call them, but actually work directly on the flagship codes. And how would you define this? What a flagship code is a different topic, but nevertheless, essentially these are relevant, well-established codes that are used by the communities involved in the project. So this is the approach we take here, instead of the dwarf approach, as I said. A little bit of what we are actually doing in this project, its conception originally from some years ago comes from grouping different people who are working in the simulation of renewable energy. So if you look at the type of people who are involved in this, you'll find fusion energy, wind farming, and of course water related power, so hydropower in particular, which is where we come in. And the approach is pretty much transverse. So all of these different flagship codes, these different communities interact with the underlying HPC modernization and HPC optimization strategy that the project intends to put forward. All right, so I will come down to business. The flagship code that we are working with in EoCoE is PowerFlow. This is essentially a three-dimensional integrated hydrological model, which means it solves the subsurface flow equation, so-called Richard's equation, and some form of a simplified surface flow equation that basically represents how water moves above the ground. It's been here for a very long time, about 40 years, but only very recently, in the past 5 years or so, was it made ready to run on GPUs with a substantial effort that was put in, which leveraged on a happen chance that PowerFlow had from the good old days when it was originally developed in the early 90s or early 80s or late 80s. This so-called embedded domain-specific language, which I will come to towards the end of the presentation again. But using this idea, it was possible to port PowerFlow to CUDA, and currently we've also been able to put PowerFlow running on top of Cocos, which allows to reach, again, the CUDA backend or the HIP backend, which we currently can use, and in principle, all other backends that Cocos exposes, but we haven't tested. Key thing is that through the previous EoCoE iterations and the work that essentially we do here in JSC, we have thoroughly demonstrated its scaling in pre-exascale systems. Now, what does Parflow actually do is kind of sketched out on the left side. If you imagine you have a landscape or a catchment, a hydrological catchment, you have some forcing, some rainfall, some evaporative demand that comes from the atmosphere, and Parflow basically solves how water moves above the ground and under the ground and how this interacts. You have an actual simulation output there in the middle, and on the right side, it's just a sketch of essentially what we're doing. So it's conceptually quite straightforward what this is doing. I would like to illustrate with the work of mainly all the other colleagues, as I said, not mine. What do we use Parflow for here in Jülich? This is a very, very shiny example that we have, this so-called water monitor. I'm sorry for the German, but it's a German project. And this is essentially a web app that allows you to consult the Parflow forecasts that are done every day here in our supercomputers, which intend to contribute to water management strategies nationwide, locally, at municipal level even. This works with a resolution of about 600 meters in latitude and longitude, so it's relatively high resolved, and you get forecasts for the next 10 days or so. So it's a bit of a helpful tool in that sense. Now, this is used in many ways, which I will not detail, but I would like to mention. So out of the forecasts, the so-called plant available water is computed. So this is what you would be interested if you have a garden or if you have crops, of course. And as I said, you have not only a short historical simulation and a short forecast, but you can actually consult this in time through the web app. You can click on the pixel, retrieve the data that is relevant for you and whatnot. There is a lot of work going downstream of this to make this deployable as an app on your smartphone, basically. So this is kind of important for agriculture in the region. As I said, again, I'm sorry for the German here, but it's just to illustrate the fact that this goes into a bulletin that is produced seasonally. So we have a projection of what we expect is going to happen seasonally in Germany in terms of these relevant variables. And all of this is basically produced by the Parflow workflows. Now, more recently, experimentally, this is also now being produced in English in a reasonably automated way. And I would also want to kind of focus on a particular aspect of it, which is stream flow generation, or if you view it from a different point, discharge forecasting. So all these points that you see on the maps of Germany there on the left, these are places where there's river gauging stations, and we can actually compare what Parflow predicts to be here you see, of course, historical runs, but what it can predict that we will have as a discharge in these stations. And this is a workflow that mutates also further, and this is actually my own work, how we use these ongoing semi-operational Parflow forecasts from which we can extract data for specific catchments, we can extract the discharge, and we push it to another model called ChEESE, which has a fully fledged shallow water solver and can do extremely high resolution flash flood modeling or large-scale flood modeling, as you can see there on the bottom left, which was an event that happened in 2021 in Germany. And the key point here is we're actually spanning the large scales of hydrology using Parflow at a reasonable resolution of about 600 meters, and the impact-based assessments with ChEESE at a very high resolution of around the meter. And this can be done with lead times that would allow for warnings and of course, management strategies. We also scale this up. We move into the continental scale, in particular in Europe. Our colleagues in the US also, of course, do this for the continental US. And the intentions are very similar. So we intend to understand water resource management at continental level. Here you see simulations that were performed at approximately 3 kilometer resolution for the pan-European domain. That's a big domain for all practical purposes. And it can be done at higher resolution, but we typically work at this resolution because we couple our work with the atmosphere, as I will show in a minute. Now, the key thing here is that at this resolution, we can resolve at least large river systems reasonably well, and water resource management strategies can be informed by these models. The other usage, I already announced it, is the coupling to to the atmospheric models. In the past, it has been the Cosmo atmospheric model. Currently, we're moving towards the Icon model. And I don't want to say much about this, but essentially the idea is that we blow up our system. So it's not only the land hydrology, but we also have the land surface and vegetation processes, and also the atmosphere that interacts, and we can fully close the hydrological cycle, which allows to move pretty much into climate scale simulations. As an example of this, well, these are actually the parflow results within the terrestrial systems modeling platform at 12-kilometer resolution, which is our current production system. And you see that the problem with this is that we don't really resolve very well these large river systems, even the really large rivers in Europe. And as we move to 3 kilometers, this is far better. And you can imagine that we would like to do this, of course, in the order of a few hundred meters, but it gets computationally very expensive. But the point here is this is really the target where we want to work, because this is where we can actually assess important events, and the natural hazards that we're concerned with water are flooding and droughts. And to give you an idea, this is the cost that we currently would have to take for a 3-kilometer integrated simulation for a full reanalysis, which is about a 30-year period, and that's about 2.5 wall time years that we would need. So it's really not feasible currently to do this at that scale. But we get more ambitious, of course, so we go to global scale simulations, in this case with parflow alone. So I leave aside these integrated simulations. And this is just a visualization of our current testing setup for global simulations at roughly 1-kilometer resolution. And this is done here in the Joules Booster supercomputer with about 80 nodes. So that's 320 A100 GPUs. It's a relatively big problem that requires some muscle. And this is the benchmark. This is our target that we're working in EcoE. So this is how I'll kind of come back to the project now. Basically, the idea in EcoE is we want to, on the one side, really enable hydropower management strategies together with parflow. Basically, use parflow as an integrator of hydrology, coupling it with a model that can simulate operations of hydropower plants. And we want to do this at a quite high resolution, potentially for a very large domain. It may be continental, it may also be worldwide. And we really have technical challenges to address with these scales. So either by making the domains larger or by making the resolution higher, or potentially by both, we start to get into our computational bottlenecks, memory bottlenecks, data storage bottlenecks, and pre and post processing bottlenecks basically all over our workflows. So you'll see that basically the work that we're trying to do in EcoE targets different parts of these workflows. Just for recognition, basically, I would like to say that in EcoE we have a lot of partners from a bunch of different institutions who have contributed strongly to the slides that I will show in a very summarized fashion in the next couple of minutes. The other point is that underneath all of this, we want to be as energy efficient as possible in our computations. First, because if we're doing environmental science, it's our main responsibility to actually be energy efficient and CO2 efficient. And this is hard with the amount of power that is required to run these simulations. And we want them to be sustainable. And this goes also into the direction of optimizing our workflows, optimizing our storage, and significantly reducing our compute footprint, if you will. So I will start with the first problem. I mentioned it last, but it's the first one I'd like to discuss. It's the problem of output and storage, and how do we post-process the data that is produced by parflow. The workflow currently, the way that we work is very straightforward. We have parflow, it produces these MPI plus CUDA simulations, and it stores a number of 3-dimensional time-dependent fields, which are what I will call the raw output. And this then goes into not very efficient Python post-processing pipelines. And this works more or less okay for the problems that we have been working in the pre-exascale era in the past 5 years or so. But as we move towards the future, the volume is so large that the impact on storage is really difficult to manage. And most importantly, when we try to open these data sets and do any kind of processing with them, the I/O bottleneck completely dominates. So the post-processing is really very light in terms of computations. So the approach that we are trying to take in ECO is to use basically a plugging layer, this thing called the PDI data interface, which fundamentally intercepts output. It instruments PowerFlow, intercepts the output, and passes it to DESA, which is developed by our colleagues in INRIA, which is a task-based approach which allows us to distribute our analytics among many nodes. The key thing here is there's 2 points that are of interest. One is that it's a very shallow invasion of the main code of PowerFlow, which is great. The other interesting thing about it is that it's very easy to integrate on the other side our existing analytics into DESA. It's all Python based, so it's straightforward to do this. And a key point here that we have not yet addressed in the project, but will be quite relevant, is if we can use the lazy CPUs which are hosting the GPU tasks on which PowerFlow is running to do these analytics, and that would be an energy optimization, essentially using those CPUs for something useful, not only to manage the GPUs. But we haven't tested this yet. We hope it will work out. Then the second level of this is that using the same technology, we will interface with the hydropower operational model. And this is just a sketch of this, how we envision this is going to work. Basically, power plants will be represented in our 12 by 12 or 3 by 3 kilometer pixels in PowerFlow as a point. Water will be removed from there as water goes into the pipe system, and then it's restituted someplace downstream. So essentially, it's a sync source interaction between the two models. And the question is, how do we make this interaction shallow, that we don't introduce a lot of clutter into the codes, and that we don't affect their performance? And this is basically what this activity will be about in EoCoE-III, together with developing a prototype which will be centered around northern Italy, the Alpine region in Italy, where our partners have a lot of expertise and have characterized the operations of these reservoirs already. We hope to then basically scale this up to continental level or something of this sort. A different set of tasks that we work with in PowerFlow have to do with improving the convergence of the matrix solvers. PowerFlow requires a linearization strategy and then a linear solve, basically, of the entire system. And it requires some smart preconditioning, especially when it comes to when you have a surface water interacting, which acts as a boundary condition on the main matrix, let's say. And this is being contributed by our colleagues in Rome, in Italy overall, through the PSC toolkit, or this parallel space computation toolkit, which attempts to provide improved and better tailored linear solvers and preconditioners for the problem that we have at hand. Currently, we're just updating our version, so we're trying to converge to something that is common. They work on top of sundials, we work on top of sundials, so this is somehow converging in this first year of project that we're working on. Now I would like to move to another issue, and I go back to the global simulations I showed a little while ago. And what you're seeing here is some of the automated instrumentation our system provides through the system called LLView. We get it for free, basically, when we run a job here in Jülich. And I'm showing two metrics here, which is the GPU utilization of those 320 GPUs. So in the vertical axis, you have the nodes in this heat map, and you have time on the horizontal axis. And in the plot below, it's the same thing, but it's memory usage. Now, as you would hope, the memory usage increases at the beginning of the job. All the memory is allocated and then remains rather constant. There's, of course, lots of fluctuations in the GPU utilization. Now, the key point, the key takeaway of this is we more or less saturate the GPUs in terms of memory, but we're not saturating them in terms of compute effort. And the reason for this is that PowerFlow has a very large memory footprint. And this is one of the big bottlenecks that we need to address in ECO. One approach that we want to try out is so-called matrix-free solvers. This implies necessarily that we have to write a new solver for this nonlinear Richards equation. And once we have this matrix-free solver, we want to compare what is the memory footprint. We would hope we would get something in the order of 50% of the reduction of the memory footprint, which would basically allow us to put twice as many cells per GPU, ideally increasing our GPU usage from something around 30% to above 60%, or even more if that is feasible. This is still quite early in the project. The plan is to use automatic code generation via exastencils, which is developed by our colleagues in University in Erlangen. And currently, the activities are to develop a prototype using a Poisson equation, which is a fundamentally much simpler equation than Richards, but that has the same structure. So we'll see how this goes, and if we can actually reduce this memory footprint, it would be a boost. Now we will move to the optimization and the performance portability of PowerFlow, which is the third axis in ECO. For context, this requires me to introduce our upcoming supercomputer here in Jülich, which you may have already know of, Jupiter, in particular the booster module, which is the GPU module. And what I'm showing here is the sketch of an NVIDIA Grace Hopper superchip, the GH200, which has these 4 green things, which are the GPUs, and these 4 blocks of ARM CPUs, each with 72 ARM cores. And Jupiter will have roughly around 24,000 of these things to achieve the exaflop that it targets. The good news is porting PowerFlow to this hardware has been very, very painless. So it's kind of already working in our demonstrator system JEDI. And what we're currently working is on something a bit more ambitious technically, and you may have seen in the previous slides when I was talking about the terrestrial systems modeling platform that we have a land surface model called CLM, and this is a code that has a very low compute effort. It has a relatively high memory footprint, and it will essentially not be ported to GPUs because it doesn't need to. But again, we have this interesting situation where we can put PowerFlow on these GPUs and CLM on these very closely linked with a very high bandwidth connection to the GPUs, these CLM tasks on the CPUs, and then again flood the node properly, maximizing its use and hopefully minimizing the energy footprint and the inefficiencies in the system. This is still ongoing. It's kind of going well, but it's a slow and a little bit painful process to ensure that we can do these in-node heterogeneous job mapping. As I said, we're currently testing, or we have tested already, PowerFlow on the Jupiter prototype called JEDI, which stands for Jupiter Exascale Development Instrument. And it means the first 48 nodes of Jupiter, which are already here in Jülich. So as I said, the effort was very minimal to port, and we get a speed up roughly of about 1.7, 1.8. So it depends on the problem that we run, which is a little bit below what other codes have been showing, but there's absolutely no optimization that has been done. It's just plug and play. The good thing, what this implies, is that when Jupiter is ready sometime in end of January, early February here in Jülich, we will be able to deploy as quickly as we get access to it. And we have a target in ECO to reach jobs that use in the order of 10,000 GPUs. So we expect to get this done quickly in Jupiter, while we are also trying to do it in parallel in Lumi, which is a different hardware, of course. It's AMD GPUs. And this takes me to really my last topic, which is the performance portability aspect, which has been ongoing with previous iterations of ECO, not only within ECO, but also with concurrent initiatives here in Germany, and brings me to the anticipated idea of the EDSL. So I mentioned already in the distant past, decades ago, this idea of the EDSL was coded in PowerFlow. This was later used in around 2020, 2021 to develop a CUDA backend, so that Parflow could be ported to CUDA. Later on, this was also used to have a Cocos backend. A couple of years ago, we did the first attempt to use the HIP backend through Cocos, and this was partially successful. And now recently, with Echo ongoing, we've managed to fully port Parflow to AMD, and we have deployed it on Lumi. I will not go into the really nasty details of how this actually works, but the concept is relatively simple. We have some macro magic, these things that you have on the right side, box loop IO, which abstract the typical 3D loop structure that you would expect in a three-dimensional numerical solver. And inside of that macro, we have something that is very similar to a lambda structure. So you pass this in your main code, and this is resolved at pre-processing time by the macro structure, which actually just abstracts this 3D loop. It's a simple the concept is very simple. The implementation is a bit convoluted, but I think it illustrates what we attempt to achieve, and how this mixes up with CUDA is you have here basically the macro definitions that we have in general terms, which are useful for other things, like not repeating this 3-line loop structure every time that you need to write a loop. You just call the box loop. Now you basically just pre-append some information before the loop body, and then your kernel launches with CUDA after you've defined it. And with Cocos is rather similar. You need also to define some kind of lambda body, and then the execution policies in Cocos. And in the end, in your main code, you always invoke box loop IO, and how this gets resolved depends on compilation flags that you pass at compilation time. The result of this has been quite promising. So we've seen a very good performance with CUDA, not as good performance with Cocos, at least not at the time when we did these plots. There's some penalty by reaching CUDA over Cocos, or at least there was. We have not done this recently again, and we're on our way to do this. And now we have also done this, as I said, on Lumi, on AMD GPUs, and we also see kind of the expected weak scaling. The largest runs that we have done so far are in the order of about 4,000 GPUs, so we are not reaching yet our 10,000 GPU target, basically because we don't have access to such large amounts of compute time in Lumi yet. We hope that we will, in the next few months, have access to the full machine and do these tests, and we will, as I said before, do them parallel in Jupyter. This is also happening together with a continuous effort to do continuous deployment and continuous benchmarking in several Euro HPC machines. So I'm just illustrating here some results that are produced by our current CDCB workflow, which runs on GitLab pipelines, Jackamar runners, and Jube underneath, and there's some code snippets of how these scripts actually look. And the idea is that we hope to be able to deploy these things in not only our systems here at JSC, but through our interaction with Echo and Castiel, actually deploy them in other machines. All right, with that, I finish. I hope this was a more or less accurate overview of what we're doing, and that it spikes your interest. And I'd be happy to take any questions.
Okay, thank you very much, Daniel. Very nice talk. Questions for Daniel? Yes, Guntram, please.
Yeah, thank you very much for this very interesting talk. I have a quite general question. You showed in the beginning a simulation in the R Valley, which is near to Jülich, and I live even nearer to that in Bonn. And as apparently we have everything in our hands to simulate such events, the question for me is, why are such tools not used? Because apparently they were not used at the time, because 150 people died in that valley during this catastrophe, and the weather forecast was there. And so where is the bottleneck? And maybe it's a more general question which applies also to other talks and tools that have been presented, but I think the question is natural.
Thanks. I mean, this is a brilliant question, I have to say. I don't think that the reasons are technical. I think you picked up on exactly what I kind of intended to suggest. So technically, we have the codes, they are performant, they are scalable, they are deployable. We probably lack still a lot of work on automated workflows, at least in our community. We're getting there with Parflow in the sense that we have these semi-operational forecasts that are produced. We don't have this yet with Sergey. We're on our way on building these workflows and connecting them with Parflow, so that if such an event were to be forecasted again by the meteorological model, the hydrological model would pick it up, and we would be able to deploy the flood model as well. But to really answer your question, I think the main reason that this is not operational is because flood management is often done at very local level. And the institutions that manage this have a much harder time to digest this new technology, which requires a lot of infrastructure. Of course, we're talking here. If you saw this was, or I think I wrote it here. This required 8 A100 GPUs, so it's not an enormous amount of a compute effort that is required. You don't need a huge supercomputer, but it's also not a toy. So I think we still lack the policies and the administrative solutions to link all these small-scale administrations. They may be, you know, statewide in Germany or below, probably below the state as well, to enable the decision makers to tap into this technology without having to go through the hurdles of developing new institutions or acquiring new hardware and deploying new expertise that is difficult to maintain. So I think HPC centers have to become at some point the place where these things are deployed, and that we just make them available easily for practitioners and for decision makers. I think that's the key factor here.
Okay, thank you a lot. I think it links also back to the question we had about urgent computing infrastructure and stuff like that before. Yeah,
absolutely. Yeah.
Yes. Okay, thank you very much. I think we should move on for the sake of time. So our next presenter is Zoltán Horváth from the Eastman University in Hungary, and he's leader in industrial mathematics, and he has extensively contributed to optimization in sectors ranging from automotive to healthcare and environmental management. So today, Zoltán will present us Hidalgo-II, which is the last center of excellence that we have today in this workshop. So please.
Thank you.
Zoltán,
thank you, Arnau.
Thank you very much.
Thank you for the introduction. I'd like to present first the Hidalgo-II Center of Excellence. I'm the work package leader for the applications. And Hidalgo-II is the Center of Excellence tackling global challenges. And first, I'd like to introduce the Hidalgo-II Center of Excellence, our goals and the environmental use cases, the Urban Air Project, which is one of the environmental use case. And we adopted our Urban Air Project to hazard use cases to the main topic of the conference, of the workshop. And I'd like to talk about these topics. You can see our partners here. PSNC is the leader, is the coordinator, and the scientific coordinator is HLRS. As I said, we are developing codes and applications for tackling global challenges. We have five use cases, 5 applications, and these are the Urban Air Project, which simulates the urban airflow in cities under very high resolution, 1 meter resolution, and also compute several business endpoints for wind comfort, air pollution, and for urban planning. The urban buildings application belongs to University of Strasbourg. They use advanced building models for computing the energy loss of buildings, and also some pollutions. The renewable energy sources belongs to PSNC, and it is for the computation of the energy production from renewable energy systems. wildfires for Meteorgrid Madrid, simulates the wildfires and interaction with its atmosphere, and FAU from Erlangen is a new partner in our consortium for the sediment and pollution transportation in waters. So let me introduce with one slide for our project applications. About this I will talk more later because we applied it for hazard addressing some hazard situations for the urban air project, and the second one, as I said, the urban building modeling, energy consumption, thermal comfort, and indoor air quality simulation. You can see here for whole city, for the buildings of a whole city, and these will be done. These are done with the different resolutions of the geometry for different level of details, and it is a validated tool. The renewable energy production simulation is consists of CAP models for mesoscale weather prediction and simulation of the geophysical flows. And as I said, and a 10-meter resolution calculates the meteorological parameters, and by using these estimate the energy production of wind farms and photovoltaic systems. The wildfires is a fully open source software, while the previous ones, some of them are contain closed components. This is for the fire spread simulation, and this is a very high tier level simulation with a very nice visualization tool, 3D visualization tool. The material transport in water is for simulating the water flow and the sediment transportation in the water by using the code Valberla, which is used by other center of excellences too. So now I'd like to go to details for our urban air project. There are many challenges around the urban airflow, namely the air pollution is very high in several cities. Also, accidental toxic gas release may have a very severe effect on health in a certain region, and we have to know where these toxic gases propagate under the urban geometry and under the predicted weather for the next future to be able to alert citizens. The pedestrian wind comfort, in particular near high buildings, extremely high buildings, can be very dangerous for people. There, the speed of the wind can be much larger than the average wind. Currently, EU provides services for example, air quality modeling, but under coarse meshes. But in cities there are local hotspots. Some of them live continuously, or rather continuously. So some part of the cities can be much less healthy than the others. On the bottom right corner, you can see one of such situation where red denotes the local hotspots for NOx, nitrogen oxides. So in our application, the main goal is to simulate an entire city with buildings, real building geometry, under very high spatial resolution, 1-2 meter resolution at street level, and make the simulation shorter than real time. And on the top of this, we want to provide this for decision makers as well. So we need an easy application environment for that, such that non-HPC users should easily apply that. These are our goals and the solution methodologies. Actually, we want to develop real-time digital twins for the airflow and air quality, which are in hazardous situation applications faster than real time to be able to pre-compute the propagation of the contaminants. So this is just one slide, one image to preview the results. This is just a part of a city. Geometry is coming from OpenStreetMap. Our application can be applied to each city which is on the OpenStreetMap, and we generate the geometry meshes and compute the wind field, and in this case we computed some statistics concerning the wind field, the low zone wind comfort. We have a workflow which gathers some data from global weather forecasts or weather simulations and traffic and building informations. So if we have traffic information, then we can simulate on HPC the propagation from traffic emissions. And we have several service endpoints, as I said, and can be seen on the right side of the slide. Let me stress one of our tools, the Matso portal, which is an automated workflow orchestration of containerized solutions with CI/CD to HPC platforms. Namely, we can configure the simulation on a web interface in a nice user environment, and we can select the domain of the city on the OpenStreetMap, and these coordinates, GPS coordinates of the corners, give as bounding box gives an input. Then we generate the geometry, the 3D geometry, and the mesh. We compute and we visualize on the web our HPC results. And just 3 slides about to illustrate the most important features of our portal. You can configure also Euro HPC machines on which to execute, deploy, and execute the codes. For example, Lumi, Meluxina can be used from this configuration session. Then you can configure your particular application, simulation time, wind condition, or whatever in this environment. And we have a dashboard. And on this dashboard, you can follow, you can monitor, you can execute, and you can follow the simulation. And we can jump into details to the log files and everything. For developers, we provide also an interface where they can write Tosca blueprints for workflow definitions. So we have to use CFD for computing the airflow, and we have 2 solvers, the OpenFOAM and the RedSim. OpenFOAM, you know OpenFOAM. We configured OpenFOAM such that and optimized such that it has a parallel efficiency above 80% on 10 million mesh number, cell number meshes. That is not necessary to go to too high number of cells to get good parallel efficiency. We ran it on 50K CPU cores with this efficiency for urban cities. The red theme is our native MPI plus GPU code. It is a native code written in C++ for the compressible Navier-Stokes and Euler equations. We apply this code not only for environmental but also industrial problems, so where compressibility was a key requirement. And we apply this MPI plus GPU code for the urban air scale, urban air pollution problems too. And we have the CFDR, our high-performance CFD visualizer. The data rendering is running on HPC and visualization from your web interface, web browser. And this runs pretty fast. Also, it supports digital twin visualization. This is the open form, just to get some impression, because lack of time, we cannot go too much into details. We are using optimized and more developed PIMP and SIMP form solvers of the code. It is used in the FAIR mode with the Forum for Air Quality Modeling in Europe. This is a activity group of member states, researchers who work for reporting according to EU directive with simulations. And on this Antwerp intercomparison exercise, we got pretty good validation results of our code. As I said, red theme is the native OpenMPI plus CUDA implementation. The same code can be used. The same source code runs on HPC and also on Windows, Linux, and each hardware. It runs the same code. It has a machine learning-based surrogate model. We use industrial standards for input-output data formats, NAS and SideGold NetCDF. And we are using NVIDIA AMGX on MPI plus GPU for implicit time stepping for the dispersion computation. This is just some slides for the comparison in a cross-section for the full order and the machine learning-based model, which is much faster. This is an application for an industrial problem for a pipe flow noise problem, an industrial application. And this is another result for the FAIR mode, what I told you, cross-sectional results about NOx propagation in the airflow plus the airflow computation. We have, as I said in the introduction, a digital twin visualization as well. That is, we can modify during running time some parameters of the code and also of the physical parameters, and code adapts to it and the visualization as well. So this is a real digital twin visualization, live visualization of the city. So going to the third chapter, addressing hazardous gas release, which is the main goal of this workshop. Our task, which is not contractual task, but we prepared for this workshop, it was on our roadmap, but we advanced it. So a precise real-time 3D prediction of chemical, biological, and radiological agent propagation in urban environments. So this is a very important problem. And there are several state-of-the-art solutions. For example, the US Navy has a code City Analyst. If you are interested, it is worth having a look to this link. where they applied it on this image sample. We can see simulations at where there was a fire near the Rockefeller Center, and they used the city analysts to predict the propagation of the gas, bird gas, which was very poisonous. And they use actually, they have to use larger dissimulation for offline simulation for the urban wind field, and they are using surrogate dispersion modeling. I am not aware of any European solution to this problem. We applied to our situation to Győr, which is the location of my university, for factory release. Sometimes factory fire can be also very poisonous, in particular if they produce batteries or something like that. And it is important to predict the propagation of the poisonous gas in time forward. And we applied it with the following way, with the OpenFOAM. This is our OpenFOAM simulation that we simulated a 2-hour propagation of this gas released from southeast to northwest, and we applied a reduced model, machine learning trained model for the steady wind field computation, and a live dispersion computation with OpenFOAM. And you can see here the covered area by gas in a cross section. This is actually a 3D simulation of the propagated gas, and it is we can see easily that it follows the change of the boundary conditions of this resulted plum, and the detailed resolution within the buildings. And for this total, we needed only this is wrong. This 4 CPU nodes. This the correct is 6 cores of 1 CPU. It runs much faster than real time, namely 15 times faster. 7 minutes was enough to compute 2 hours in advance. So it is applicable, but the drawback of this solution is that we have to have a pre-trained model for the city, which takes time. So the pre-processing time is large, but we have a workflow for that. The other solution with RedSim needs also some pre-computed time, similarly a city analyst. We are doing on Carolina with our GPU on a GPU cluster. We computed high resolution wind field, steady wind fields, and we used those and live implicit time stepping simulation on one GPU, NVIDIA GPU. That was enough. We wanted to run it on a simple hardware to be able to provide it for decision makers. This was on one NVIDIA GPU, which might be easily accessible for anyone recently. And in total, we got 6 times faster than real time. And we acknowledge the Hungarian NCC for providing us GPU resources for the development, and we are ready for any collaborations with NCCs or COEs. We would be very glad to have mesoscale weather models or to cope with or to apply our tools to any cities which are on the OpenStreetMap. Thank you.
Thank you so much, Zoltán. Very nice results that you show us. Questions? I think we are all a bit tired. Very nice. Just very quick, if you can answer in just in 1 minute, in this simulation, pre-run simulations that you have shown, that you just have simulations varying 2 degrees. No, I understand the income incidence angle of the wind. Do you take into account also the atmospheric stratification, the different conditions that you might have for stable and unstable?
Not yet, but it's on the roadmap, on the closed roadmap.
Perfect. Thank you. Okay, Tomaso, quickly, please.
Yes, very quick. Thank you, Zoltán. Quick question about the OpenFOAM. Which release of OpenFOAM are you using? The ESI or the Foundation release?
Yes, the fully open source release, yeah.
Okay. Have you had an interaction about the performance of OpenFOAM with the Foundation? Because we have been facing the optimization of OpenFOAM for many years now in ChEESE, and okay, we are very keen to interact if you have experience.
Yeah, we would be glad to doing so. This was a collaboration with HLRS, with Accelerat, actually. But Tomaso, we would be really glad to collaborate with you.
Okay, we'll be in touch. Okay.
Thank you.
Okay. Thank you very much. I don't see any other question neither in the chat. So let's move to the last question, the last presentation. This is a bit shorter, but Mirta Rodriguez, she's from Mitiga Solutions, a data science lead from Mitiga Solutions, and she will talk us about bridging science and business and showcase the case of Mitiga. So thank you for waiting, Mirta. The floor is yours.
Okay, I'm trying to share my screen.
Yes, you are sharing.
I'm sharing. Am I in presenter mode? Yes. Okay.
Perfect. Thank you.
Okay, thank you very much. Thanks very much to the organizers for inviting us here today, and also for the audience that is still here at this time of the day. So I will be very quick. I was advised to prepare a non-technical presentation, so I followed that. So I will just show you an overview of what we do here at Mitiga Solutions. So, and how we bridge science and business. Okay, so we are a spin-off from the from the Barcelona Supercomputing Center. We are currently 70+ people. 40% of us have a PhD, and we closed our Series A, our round of funding, last year, and we are invested by Microsoft and Telefónica and others. So most of our product, our main product, is stored in Azure. But there are lots of things that we still use, and we use Mare Nostrum 5 for. So what is our mission, our vision? We are a climate tech, so our vision is to become the global leader in climate physical risks across the energy, real estate, insurance, and reporting sectors. Okay, so what do we actually do? We have 2 main lines of activity. On the one hand, we provide climate risk analysis through our platform. This is EarthScan. This is a SaaS platform, and that allows customers to analyze, report, and act on their exposure to climate risk. So for this, we have maybe half of the company working around this. We have a commercial team, we have a tech team that supports this. And in addition to this product, we have a team of scientists and data scientists that we are working on risk modeling. And we are trying to develop extreme weather and wildfire risk modeling at high resolution. We combine here AI and high performance computing, and this is what relates most to this presentation. But before that, I wanted to briefly show what is EarthScan. EarthScan is a platform where clients can load their assets. So they have a portfolio of assets, and they can analyze how they will be impacted by climate risk. It is a global product. It has a ERA 5 resolution, so 25 kilometer resolution, more or less, and results are retrieved in very short time, in few seconds. So we include in our platform several hazard types, most of them related to atmospheric signals, so heat stress, drought, wildfires, extreme wind and precipitation. And in addition to that, we have wildfires and flooding. All of the atmospheric ones are based on CMAP6 data that is downscaled to ERA 5 and is at the ERA 5 resolution. Flooding, of course, is at much higher resolution, which is 60 meters, I think. We have included 3 different climate scenarios, and we produce results. We show results from 1970s to 2100. Here a video, which I'm hoping will work on our platform. It's very short, so no worries. I will lower the volume. So just for you to see what the interface, how they look. So this is the interface that the customer can see. The assets are located worldwide. We provide the results on risk on a ratings score, which goes from A to F. Client can move across years, and they can understand a physical risk of the individual hazards and also the combined physical risk. And they can download and get a report on the result. Okay, so this is the product team, the main product. Oh, sorry. How do I go to the next slide now without messing up? I'm gonna, okay, and present. I'm beginning, sorry. Oh. Okay, so what do we do? The rest of the team, we are working on risk modeling, and this is powered by European projects. So research and innovation is one of the main activities we do as well here in Mitiga, and I'm going to showcase 2 of the projects and explain what we are doing there. One of them is ChEESE. This is a project that was funded. It is funded by the European Defence Fund, where we develop machine learning and other AI approaches for secure, robust, frugal, and explainable solutions for defense. This is coordinated by a large company, an engineering company, a Spanish one here in Madrid, and we have here several RTOs. One of them is BSC, and there are several teams of BSC working here, and one of them we closely collaborate on our use case. We have results validated by LNE, which is the meteorological institution in France. I will briefly show our use case. We are work package leaders, but as well we have a use case that we are leading, and it is around atmospheric hazard mapping. What is the link to this sector is adverse meteorological conditions can strongly affect logistics and mission planning, but for us, what do we plan and promise to deliver are hail and convection hazard maps for the region of interest. Okay, so how do we do? Briefly, the methodology that we are employing is a hybrid approach where we combine numerical weather prediction models and machine learning. It's a 2-step approach. In the first one, the first part of the methodology is a machine learning tool that helps us screen days with high probability of developing a storm. In this way, we don't need to run launch simulations for every day of the season. So we launch only simulations on the days that have a high probability of convection. So on the right-hand side, you see the results. This is the climatology for the last 40 years on the number of hail days in the region of interest. And then we choose specific region. In this case, is the Catalonian area. And left-hand side results are on ERA 5 scale. We have this machine learning part at the ERA 5 resolution. Then when we want to downscale and analyze hail at the proper resolution, which in this case is 1 kilometer, we need Mare Nostrum 5 facilities in order to run our simulations. So these are preliminary results we have here in the project. This is a 3-year project. We are currently finishing year 2, and we will last year dedicate to classify sizes and also discuss with stakeholders on how the use of this product can be. This is the second project I wanted to show briefly is Carmine. It is a climate resilient development pathways in metropolitan regions of Europe. This project is huge. We are over 30 partners, 28 of them European, and it runs mainly the main goal is to help and assist metropolitan communities to become climate resilient and address the charter of the EU mission on adaptation. It is focused on the years 2030 to 2050, and it needs to run at the resolution that is required on this metropolitan area. So we have the two challenges here. We have the climate projections plus the high resolution. The project is founded around three main pillars. Main one is co-creation and co-development and working closely with regional communities. So we have a lot of activities with the regional stakeholders, and final goal is to deliver scientific tools for decision making. This is a picture of last week's Living Lab activities we had here in Catalonian area, and I have to say that there is quite a big engagement from the local stakeholders. So what was decided? What's the main goal of our case study in Barcelona, in the Barcelona metropolitan region? So the goal is to understand wildfires risk and the interface between drought and heat waves and wildfire risk on the period of interest for this for the project, which is 2030 to 2050. Here we saw that, well, this metropolitan region comprises 9 municipalities plus natural park and lots of dense wildland around the area. And we have here historical, some results from a parallel project we are running with our colleagues at BSc, which is SALUS, is a national project where we have calculated wildfire susceptibility based on burnt area. And these are the results we have at, this is the starting point for us at 500-meter resolution. Okay, so how are we gonna address this? How are we gonna deliver droughts, heat waves indicators at the resolution required for the climate projection? On the one hand, we are gonna work we are gonna reuse a downscaling pipeline that we have operational. We have in Mare Nostrum 5. We are using this to downscale at the minute meteorological data. So we are downscaling ERA 5 data into WRF data at 4 kilometers. This is an example of 2-meter temperature, but we are downscaling multiple variables. And we will reuse this pipeline for downscaling climate data, most likely Cordex data into MO1 data. So that's the goal. That's the part of the droughts and heat wave indicators. How we will address risk, wildfire risk. We have quite a bit of experience here. We're running fire spread simulations where we run Farsight. We have it here at Mitiga. We've been working with that for quite a while, and we will combine this with machine learning for wildfire susceptibility or ignition point susceptibility. So this is the plan. This is a project that is currently at month 6, and we still have few months to go. I've seen that many people have discussed here similar wildfire problems. So I think this is I think we are very keen on discussing any approaches that we could and any synergies we could find. So that was all that I wanted to say today. Thanks very much again for the invitation, and that we are open to synergies and collaborations, either through these projects or the projects presented here or new ones. Thank you very much.
Thanks to you, Mirta. Thank you very much. Questions or comments? Guntram?
Yeah, one question in what are your, it's a very nice presentation, and it's maybe the bridge from what we have seen before and to potential users outside the let's say the scientific bubble. And what are your intended customers? I seem to have taken from your presentation, it's mostly maybe municipalities or public authorities, or it's wider?
That's within European projects. Those are the stakeholders we talk to, but actually those are very difficult for us to reach for an SME. So our customers for our platform are usually large corporations in financial, like hedge funds, investors that are analyzing climate risks. So that's one. For the high resolution models, we are talking lots with renewable energy companies and insurance companies. Those are the two main, as well as real estate. We have some work with them on heat and heat indicators and comfort. So those are our customers. But municipalities are stakeholders in our projects, but for us, we don't get them as customers. You know, like it's we collaborate with them in projects. We wouldn't mind, but I think it's not yet at the level.
Okay, yeah, thank you. Quite interesting.
Thank you. Any other question? No? Okay. If not, I just want to thank you, all the speakers, first of all, for that very nice presentation. I think, it has been a bit dense and long, but super interesting, at least for me. So thank you very much to all the speakers and also to the audience. And I hope that the event has been useful. Thanks again to Ayrton and Barbara for organizing this. And that's it. Let's keep in touch, and I hope that at least some synergies emerge from the different applications and projects that we have seen today. So that's it from my side. Thank you very much.
Thank you very much.
Thank you.